is, for example, the weekends or the nights or things like that.
Are time reversed forms. That the electron and the positron is just the electron moving backwards in time. Another way to look at it is that that gravity itself is just pressure. It's just pressure. And you can have a negative pressure differential and a positive pressure differential. You can have either repulsion or attraction. And that can be represented in forms of negative energy. If that doesn't make sense, don't worry, because there's going to be more right here. Okay.
So Dirac did what Dirac does best, and he set out to find his own solution that contained no second-order time derivatives. First,
so Dirac basically does a whole bunch of math, chat. Dirac does a whole bunch of math, and he's like, I need to be able to solve this in a way that'll make sense. And what does he do? Dirac goes and he makes a matrix. Dirac says, okay, what we can do is we can write this as a matrix form. Because the matrix form will take into account which vector goes first. And if you write this in a matrix form, now you can accurately represent how the wave functions operate. That's what Dirac does. Does a whole bunch of math, basically figures out this is how we can get the waveforms to work, but you need to create a matrix. And the matrix is representing spatial directions. So I think I explained that correctly. Let me go to this Yahtzee moment here. 1 second, chat. Okay, 21 minutes. My boy Heisenberg was in there. Yeah, so here you go. Here's the matrix part. I'm going to play at higher speed here for you guys. Oops. Shit.
Were satisfied. Dirac had found coefficients that worked. Now, we can substitute those matrices back into Dirac's linear equation, then rewrite the three momenta and alpha coefficients as vectors. And, just as we did with the Schrodinger and Klein-Gordon equations, we can use the energy and momentum operators to make both sides act on the wave function. If we substitute those operators in, we get Dirac's final equation for the relativistic free electron.
Hold up. What did he just say? Wait, what math did this just solve? So, I kind of skipped through this, but I just explained that Dirac took Schrodinger's equation, applied a matrix form to it to get rid of these squares so that we won't have a positive and minus solution. And what did that create? What did this equation create? This equation creates...
We get Dirac's final equation for the relativistic free electron.
Relativistic free electron. Holy crap. Holy shit. The relativistic free electron? That's the solution? That's what we've been solving. It makes so much sense because what are we saying? We're saying this equation represents the movement of an electron through the atom's orbital. This explains how the electron moves in presence of another electromagnetic field from the atom itself. And this equation gives us what would happen if we had free electrons. And what is, anybody in the chat, what is the secret to our fusion reactors? are field reverse configuration fusion reactors relativistic free electron lasers. That can't be a coincidence. There's no way that this is a coincidence. 0% chance. When I heard him say free electron lasers, I actually cried. I cried a little bit. Tears came down my eyes because I went, holy shit, this is the answer. They solved the Schrodinger equation. They solved the Dirac equation. And they figured out how to use high-powered lasers to manipulate the vacuum, to make the vacuum form geometrical shapes. Because once you've solved that equation, you can now control the movement of any atom and mass in our reality. You can solve the instabilities in plasma. All the plasma issues we have with instabilities in fusion, solved. That's what the equation means. That's what the equations tell us. They tell us how electrons are going to move at the quantum scale. And there it is. The free electron equation. Boom. Yes, you can control gravity with this equation. You can control gravity. That's the craziest thing to me. You can literally control gravity. That's what they figured out. When they figured out how to manipulate free electrons, move electrons around freely, control them through 4-dimensional, 5-dimensional space, they've now figured out how to control gravity. That's the underlying basis for it, right there. Electromagnetism, hydrodynamics, magnetohydrodynamics. Unbelievable. Okay, a few more clips here, guys, from this. Great video. If you guys want to learn more about Dirac and the Schrodinger equation, the history of Heisenberg. By the way, Heisenberg was the mentor to Friedwart Winterberg, the nuclear scientist whose textbook I read. Do I keep talking about? Heisenberg. Werner Heisenberg was his mentor in Germany. Can't make this shit up, chat. Cannot make this stuff up. I wish I could make this up. I wish I could make up a story this good. Okay, let's skip ahead a few minutes here. So amazing, honestly.
Possible states due to different orientations of its intrinsic angular momentum. Spin up and
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, again, welcome to 1801. We're getting started today with what we're calling Unit 1, highly imaginative topic, highly imaginative title, and it's differentiation. So let me first tell you briefly what's in store in the next couple of weeks. The main topic today is what is a derivative. And we're going to look at this from several different points of view. And the first one is the geometric interpretation. And that's what we'll spend most of today on. And then we'll also talk about a physical interpretation of what a derivative is. And then there's going to be something else which I guess is maybe the reason why calculus is so fundamental and why we always start with it in most science and engineering schools, which is the importance of derivatives of this to all measurements. So that means pretty much every place. That means in science, in engineering, in economics, in political science, etc. Polling, lots of commercial applications, just about everything. Now, so that's what we'll be getting started with. And then there's another thing that we're going to do in this unit, which is we're going to explain how to differentiate anything. So how to differentiate any function you know. And that's kind of a tall order, but let me just give you an example. If you want to take the derivative, this we'll see today as the notation for the derivative of something, of some messy function like e to the x arctan of x, we'll work this out by the end of this unit. All right? So anything you can think of, anything you can write down, we can differentiate it. All right, so that's what we're going to do. And today, as I said, we're going to spend most of our time on this geometric interpretation. So let's begin with that. So here we go with the geometric interpretation of derivatives. And what we're going to do is just ask the geometric problem of finding the tangent line to some graph of some function at some point, which is, say, x0, y0. So that's the problem that we're addressing here. I guess I should probably turn this off. All right. So here's our problem. And now let me show you the solution. So, well, let's graph the function. So let's say here's its graph. And here's some point. All right. Maybe I should draw it just a bit lower so that I don't. All right, so here's a point P. Maybe it's above the point x0. x0, by the way, this was supposed to be an x0. That was some fixed place on the x-axis. And now, in order to perform this mighty feat, I will use another color of chalk. How about red? Okay, so here it is. There's the tangent line. Well, not quite straight, close enough. All right, I did it. All right, that's the end. That's the geometric problem. I achieved what I wanted to do. And it's kind of an interesting question, which unfortunately I can't solve for you in this class, which is how did I do that? That is, how physically did I manage to know what to do? to draw this tangent line, but that's what geometric problems are like. We visualize it, we can figure it out, somewhere in our brains it happens. And the task that we have now is to figure out how to do it analytically, to do it in a way that a machine could do just as well as I did in drawing this tangent line. So what did we learn in high school about what a tangent line is? Well, a tangent line has an equation. Any line through a point has the equation y minus y0 is equal to m, the slope, times x minus x0. So here's the equation for that line. And now there are two pieces of information that we're going to need to work out what the line is. The first one is the point. That's that point P there. And to specify P, given x, we need to know the level of y, which is, of course, just f of x0. Now, that's not a calculus problem, but anyway, that's a very important part of the process. So that's the first thing we need to know. And the second thing we need to know is the slope. And that's this number m. And in calculus, we have another name for it. We call it f prime of x0, namely the derivative of f. So that's the calculus part, that's the tricky part, and that's the part that we have to discuss now. So just to make that explicit here, I'm going to make a definition, which is that f prime of x0, which is known as the derivative of f at x0, all right, is the slope of the tangent line to y equals f of x at the point, let's just call it P. All right? So that's what it is, but still I haven't made any progress in figuring out any better how I drew that line. So I have to say something that's more concrete because I want to be able to cook up what these numbers are. I have to figure out what this number m is. And one way of thinking about that, let me just try it, is, so I certainly am taking for granted that in the sort of non-calculus part that I know what a line through a point is. So I know this equation. But another possibility might be, this line here. How do I know? Well, unfortunately, I didn't draw it quite straight, but there it is. How do I know that this orange line is not a tangent line, but this other line is a tangent line? Well, it's actually not so obvious, but I'm going to describe it a little bit. It's not really the fact, this thing crosses at some other place, which is this point Q, but it's not really the fact that the thing crosses at two places, because the line could be wiggly, the curve could be wiggly, and it could cross back and forth a number of times. That's not what distinguishes the tangent line. So I'm going to have to somehow grasp this, and I first do it in language. And it's the following idea. It's that if you take this orange line, which is called a secant line, and you think of the Q, the point Q is getting closer and closer to P, then the slope of that line will get closer and closer to the slope of the red line. And if we draw it close enough, then that's going to be the correct line. So that's really what I did sort of in my brain when I drew that first line. And so that's the way I'm going to articulate it first now. So the tangent line is equal to the limit of what so-called secant lines, PQ, as Q tends to P. And here we're thinking of P as being fixed and Q as varying. All right, so that's again, this is still a geometric discussion, but now we're going to be able to put symbols and formulas to this computation, and we'll be able to work out formulas in any example. So let's do that. So first of all, I'm going to write out these points P and Q again. So maybe we'll put P here and Q here. And I'm thinking of this line through them. I guess it was orange, so we'll leave it as orange. All right. And now I want to compute its slope. And so this will gradually, we'll do this in 2 steps, and these steps will introduce us to the basic notations which are used throughout calculus, including multivariable calculus, across the board. So the first notation that's used is, you imagine here's the x-axis underneath, and here's the x0, the location directly below the point P. And we're traveling here a horizontal distance, which is denoted by delta x. So that's delta x, so-called. And we could also call it the change in x. All right, so that's one thing we want to measure in order to get the slope of this line PQ. And the other thing is this height. So that's this distance here, which we denote delta f, which is the change in f. And then the slope is just the ratio delta f over delta x. So this is the slope of the secant. And the process I just described over here with this limit applies not just to the whole line itself, but also in particular to its slope. And the way we write that is the limit as delta x goes to 0, and that's going to be our slope. So this is the slope of the tangent line. Okay, now this is still a little general, and I want to work out a more usable form here. I want to work out a better formula for this. And in order to do that, I'm going to write delta f, the numerator, more explicitly here, the change in f. So remember that the point P is the point x0, f of x0. All right, that's what we got from our formula for the point. And in order to compute these distances, and in particular the vertical distance here, I'm going to have to get a formula for Q as well. So if this horizontal distance is delta x, then this location is x0 plus delta x. And so the point above that point has a formula, which is x0 plus delta x, f of, and this is a mouthful, x0 plus delta x. All right, so there's the formula for the point Q. Here's the formula for the point P. And now I can write a different formula for the derivative, which is the following. So this f prime of x0, which is the same as m, is going to be the limit as delta x goes to 0 of the change in f. Well, the change in f is the value of f at the upper point here, which is x0 plus delta x, and minus its value at the lower point, p, which is f of x0, divided by delta x. All right, so this is the formula. I'm going to put this in a little box because this is by far the most important formula today, which we use to derive pretty much everything else. And this is the way that we're going to be able to compute these numbers. So let's do an example. This example, so we'll call this example 1. We'll take the function f of x, which is 1 over x. That's sufficiently complicated to have an interesting answer and sufficiently straightforward that we can compute the derivative fairly quickly. So what is it that we're going to do here? All we're going to do is we're going to plug in this formula here for that function. That's all we're going to do. And visually, what we're accomplishing is somehow to take the hyperbola and take a point on the hyperbola and figure out some tangent line. All right, that's what we're accomplishing when we do that. So we're accomplishing this geometrically, but we'll be doing it algebraically. So first, we consider this difference, delta f over delta x, and write out its formula. So I have to have a place, so I'm going to make it, again, above this point x0, which is a general point. We'll make the general calculation. So the value of f at the top, when we move to the right by f of x, so I just read off from here the formula. The first thing I get here is 1 over x0 plus delta x. That's the left-hand term, minus 1 over x0. That's the right-hand term. And then I have to divide that by delta x. Okay, so here's our expression. And by the way, this has a name. This thing is called a difference quotient. It's pretty complicated because there's always a difference in the numerator, and in disguise the denominator is a difference because it's the difference between the value on the right side and the value on the left side here. Okay, so now we're going to simplify it by some algebra. So let's just take a look. So this is equal to, let's continue on the next level here. This is equal to 1 over delta x times, now all I'm going to do is put it over a common denominator. So the common denominator is x0 plus delta x times x0. And so in the numerator for the first expression, I have x0. And for the second expression, I have x0 plus delta x. So this is the same thing as I had in the numerator before, factoring out this denominator. And here I put that numerator into this more amenable form. And now there are two basic cancellations. The first one is that x0 and x0 cancel. So we have this. And then the second step is that these two expressions cancel, right? The numerator and denominator. Now we have a cancellation that we can make use of. So we'll write that under here. And this is equals minus 1 over x0 plus delta x times x0. And then the very last step is to take the limit as delta x tends to 0. And now we can do it. Before we couldn't do it. Why? Because the numerator and the denominator gave us 0 over 0. But now that I've made this cancellation, I can pass to the limit. And all that happens is I set this delta x equal to 0, and I get minus 1 over x0 squared. All right, so that's the answer. All right, so in other words, what I've shown, let me put it up here, is that f prime of x0 is minus 1 over x0 squared. Now, let's look at the graph just a little bit to check this for plausibility, all right? What's happening here is, first of all, it's negative, right? It's less than 0, which is a good thing. You see that slope there is negative. That's the simplest check that you could make. And the second thing that I would just like to point out is that as x goes to infinity, that is, as we go farther to the right, it gets less and less steep. So less, and whoops, as x0 goes to infinity, not 0. As x0 goes to infinity, less and less steep. So that's also consistent here. When x0 is very large, this is a smaller and smaller number in magnitude, although it's always negative. It's always sloping down. All right. So I've managed to fill the boards, so maybe I should stop for a question or two. Yes? So the question is to explain again this limiting process. So the formula here is we have basically two numbers. So in other words, why is it that this expression, when delta x tends to 0, is equal to minus 1 over x0 squared? Let me illustrate it by sticking in a number for x0 to make it more explicit. All right? So for instance, let me stick in here for x0 the number 3. Then it's minus 1 over 3 plus delta x times 3. That's the situation that we've got. And now the question is, what happens as this number gets smaller and smaller and smaller and gets to be practically 0? Well, literally what we can do is just plug in 0 there. Then you get 3 plus 0 times 3 in the denominator, minus 1 in the numerator. So this tends to minus 1 over 9, over 3 squared. And that's what I'm saying in general with this extra number here. Other questions? Yes?
How do you simplify from delta f over delta x? How do you simplify from the original equation to 1 over delta x factored out?
So the question is, what happened between this step and this step, right? Explain this step here. All right? So there were two parts to that. The first is this delta x, which was sitting in the denominator, I factored all the way out front. And so what's in the parentheses is supposed to be the same as what's in the numerator of this other expression. And then, at the same time as doing that, I put that expression, which is a difference of two fractions, I expressed it with a common denominator. So in the denominator here, you see the product of the denominators of the two fractions, and then I just figured out what the numerator had to be, without really, other questions? Okay, so now, I claim that on the whole, calculus gets a bad rap, that it's actually easier than most things, but there's a perception that it's harder, and so I really have a duty to give you the calculus made harder story here. So we have to make things harder because that's our job. And this is actually what most people do in calculus, and it's the reason why calculus has a bad reputation. So the secret is that when people ask problems in calculus, they generally ask them in context. And there are many, many other things going on. And so the little piece of the problem, which is calculus, is actually fairly routine and has to be isolated and gotten through. But all the rest of it relies on everything else you learned in mathematics up to this stage, from grade school to through high school. So that's the complication. So now we're going to do a little bit of calculus made hard. By talking about a word problem. Now, we only have one sort of word problem that we can pose because all we've talked about is this geometry point of view. So far, those are the only kinds of word problems we can pose. So what we're going to do is just pose such a problem. So find the areas of triangles enclosed by the axes and the tangent to y equals 1 over x. Okay? So that's a geometry problem. And let me draw a picture of it. It's practically the same as the picture for example 1, of course. So we'll only consider the first quadrant. Here's our shape. All right, it's the hyperbola. And here's maybe one of our tangent lines, which is coming in like this. And then we're trying to find this area here. All right, so there's our problem. So why does it have to do with calculus? It has to do with calculus because there's a tangent line in it. And so we're going to need to do some calculus to answer this question. But as you'll see, the calculus is the easy part. So let's get started with this problem. First of all, I'm going to label a few things. And one important thing to remember, of course, is that the curve is y equals 1 over x. That's perfectly reasonable to do. And also, we're going to calculate the areas of the triangles. And you could ask yourself, in terms of what? Well, we're going to have to pick a point and give it a name. And since we need a number, we're going to have to do more than geometry. We're going to have to do some of this analysis, just as we've done before. So I'm going to pick a point. And consistent with the labeling we've done before, I'm going to call it x0, y0. So that's almost half the battle. Having notations, x and y for the variables, and x0 and y0 for the specific point. Now, once you see that you have these labelings, I hope it's reasonable to do the following. So first of all, this is the point x0, and over here is the point y0. That's something that we're used to in graphs. And in order to figure out the area of this triangle, it's pretty clear that we should find the base, which is that we should find this location here, and we should find the height, so we need to find that value there. All right, so let's go ahead and do it. So how are we going to do this? Well, so let's just take a look. So what is it that we need to do? I claim that there's only one calculus step, and I'm going to put a star here for this tangent line. I have to understand what the tangent line is. And once I figured out what the tangent line is, the rest of the problem is no longer calculus. It's just that slope that we need. So what's the formula for the tangent line? Put that over here. It's going to be y minus y0 is equal to, and here's the magic number. We already calculated it. It's in the box over there. It's minus 1 over x0 squared, x minus x0. So this is the only bit of calculus in this problem. But now we're not done. We have to finish it. We have to figure out all the rest of these quantities so we can figure out the area. All right. So how do we do that? Well, to find this point, this has a name. We're going to find the so-called x-intercept. That's the first thing we're going to do. So to do that, what we need to do is to find where this horizontal line meets that diagonal line. And the equation for the x-intercept is y equals 0. All right? So we plug in y equals 0, that's this horizontal line, and we find this point. So let's do that into star. So we get 0 minus, one other thing we need to know. We know that y0 is f of x0, and f of x is 1 over x. So this thing is 1 over x0. Right? And that's equal to minus 1 over x0 squared, and here's x, and here's x0. All right? So in order to find this x value, I have to plug in one equation into the other. So this simplifies a bit. Let's see, this is minus x over x0 squared, and this is plus 1 over x0, because the x0 and x0 squared cancel somewhat. And so if I put this on the other side, I get x divided by x0 squared is equal to 2 over x0. And if I then multiply through, so that's what this implies, and if I multiply through by x0 squared, I get x is equal to 2x0. Okay? Okay, so I claim that this point we've just calculated, it's 2x0. Now, x of minus of x star. This horizontal line, well, to find this point, this has a name. We're going to find the so-called x-intercept. That's the first thing we're going to do. So to do that, what we need to do is to find where this horizontal line meets that diagonal line. And the equation for the x-intercept is y equals 0. All right? So we plug in y equals 0, that's this horizontal line, and we find this point. So let's do that into star. So we get 0 minus, one other thing we need to know. We know that y0 is f of x0, and f of x is 1 over x. So this thing is 1 over x0. Right? And that's equal to minus 1 over x0 squared, and here's x, and here's x0. All right? So in order to find this x value, I have to plug in one equation into the other. So this simplifies a bit. Let's see, this is minus x over x0 squared, and this is plus 1 over x0, because the x0 and x0 squared cancel somewhat. And so if I put this on the other side, I get x divided by x0 squared is equal to 2 over x0. And if I then multiply through, so that's what this implies, and if I multiply through by x0 squared, I get x is equal to 2x0. Okay? Okay, so I claim that this point we've just calculated, it's 2x0. Now, I'm almost done. I need to get the other one. I need to get this one up here. Now, I'm going to use a very big shortcut to do that. So the shortcut to the y-intercept, the y-intercept, is to use symmetry. All right, I claim I can stare at this, and I can look at that, and I know the formula for the y-intercept. It's equal to 2y0. All right, that's what that one is. So this one is 2y0. And the reason I know this is the following. So here's the symmetry of the situation, which is not completely direct. It's a kind of mirror symmetry around the diagonal. It involves the exchange of xy with yx. So trading the roles of x and y. So the symmetry that I'm using is that any formula I get that involves x's and y's, if I trade all the x's and replace them by y's and trade all the y's and replace them by x's, then I'll have a correct formula on the other way. So everywhere I see a y, I make it an x, and everywhere I see an x, I make it a y. The switch will take place. So why is that? That's because that's just an accident of this equation. That's because, so the symmetry explained. Is that the equation is y equals 1 over x, but that's the same thing as xy equals 1, if I multiply through by x, which is the same thing as x equals 1 over y. So here's where the x and the y get reversed. Okay, now if you don't trust this explanation, you can also get the y-intercept by plugging x equals 0 into the equation star. Okay? We plugged y equals 0 in, and we got the x value. And you could do the same thing analogously the other way. All right, so I'm almost done with the geometry problem, and let's finish it off now. Well, let me hold off for 1 second before I finish it off. What I'd like to say is just make one more tiny remark, all right? And this is the hardest part of calculus, in my opinion. So the hardest part of calculus is that we call it one variable calculus, but we're perfectly happy to deal with 4 variables at a time, or 5, or any number. In this problem, I had an x, a y, an x0, and a y0. That's already 4 different things. They have various interrelationships between them. So, of course, the manipulations we do with them are algebraic, and when we're doing the derivatives, we just consider what's known as one variable calculus. But really, there are millions of variables floating around, potentially. So that's what makes things complicated, and that's something that you have to get used to. Now, there's something else which is more subtle, and that I think many people who teach the subject or use the subject aren't aware, because they've already entered into the language, and they're so comfortable with it that they don't even notice this confusion. There's something deliberately sloppy about the way we deal with these variables. The reason is very simple. There are already 4 variables here. I don't want to create 6 names for variables or 8 names for variables. But really in this problem, there were about 8. I just slipped them by you. So why is that? Well, notice that the first time that I got a formula for y0 here, it was this point, And so the formula for y0, which I plugged in right here, was from the equation of the curve, y0 equals 1 over x0. The second time I did it, I did not use y equals 1 over x. I used this equation here. So this is not y equals 1 over x. That's the wrong thing to do. That's an easy mistake to make if the formulas are all a blur to you and you're not paying attention to where they are on the diagram. You see, that y-intercept, that x-intercept calculation there involved where this horizontal line met this diagonal line, and y equals 0 represented this line here. So the sloppiness is that y means two different things. And we do this constantly because it's way, way more complicated not to do it. It's much more convenient for us to allow ourselves the flexibility to change the role that this letter plays in the middle of the computation. And similarly, later on, if I had done this by this more straightforward method for the y-intercept, I would have set x equal to 0. That would have been this vertical line, which is x equals 0. But I didn't change the letter x when I did that, because that would be a waste for us. So this is one of the main confusions that happens. If you can keep yourself straight, you're a lot better off. And as I say, this is one of the complexities. All right. So now let's finish off the problem. Let me finally get this area here. So actually, I'll just finish it off right here. So the area of the triangle is, well, it's the base times the height. The base is 2x0, the height is 2y0, and a half of that. So it's a half 2x0 times 2y0, which is 2x0, y0, which is, lo and behold, 2. So the amusing thing in this case is it actually didn't matter what x0 and y0 are. We get the same answer every time. Now, that's just an accident of the function 1 over x. Happens to be the function with that property. All right. So we still have more business today, some serious business. So let me continue. So first of all, I want to give you a few more notations. And these are just other ways that people notations that people use to refer to derivatives. And the first one is the following. We already wrote y is equal to f of x. And so when we write delta y, that means the same thing as delta f. That's a typical notation. And previously, we wrote f prime for the derivative. So this is Newton's notation for the derivative. Okay? But there are other notations, and one of them is df dx. And another one is dy dx, meaning exactly the same thing. And sometimes we let the function slip down below, so that becomes d by dx of f, or d by dx of y. So these are all notations that are used for the derivative, and these were initiated by Leibniz. And these notations are used interchangeably, sometimes practically together. They both turn out to be extremely useful. This one omits, notice that this thing omits the underlying base point, x0. That's one of the nuisances. It doesn't give you all the information, but there are lots of situations like that where people leave out some of the important information. You have to fill it in from context. So that's another couple of notations. So now I have one more calculation for you today. I carried out this calculation of the derivative of the the derivative of the function 1 over x, I want to take care of some other powers. So let's do that. So example 2 is going to be the function f of x is x to the n equals 1, 2, 3, one of these guys. And now what we're trying to figure out is the derivative with respect to x of x to the n in our new notation, what this is equal to. So again, we're going to form this expression delta f delta x, and we're going to make some algebraic simplification. So what we plug in for delta f is x plus delta x to the n minus x to the n divided by delta x. Now before, well, let me just stick this in and I'm going to erase it. Before I wrote x0 here and x0 there. But now I'm going to get rid of it, because in this particular calculation it's a nuisance. I don't have an x floating around, which means something different from the x0, and I just don't want to have to keep on writing all those symbols. It's a waste of Blackboard energy. There's a total amount of energy that I've already filled up so many Blackboards that it's just a limited amount of, plus I'm trying to conserve chalk. Okay, anyway, no zeros. So think of x as fixed. Again, in this case, delta x moves and x is fixed in this calculation. All right, now, in order to simplify this, in order to understand algebraically what's going on, I need to understand what the nth power of a sum is. And that's a famous formula. We only need a little tiny bit of it, called the binomial theorem. So the binomial theorem, which is in your text and explained in an exercise, says, in an appendix, says that if you take the sum of two guys and you take them to the nth power, that of course is x plus delta x multiplied by itself n times. And so the first term is x to the n. That's when all of the n factors come in. And then you could have this factor of delta x and all the rest x's. So at least one term of the form x to the n minus 1 times delta x. And how many times does that happen? Well, it happens when there's a factor from here, from the next factor, and so on and so on and so on. There's a total of n possible times that happens. And now the great thing is that with this alone, all the rest of the terms are junk that we won't have to worry about. So to be more specific, the junk, there's a very careful notation for the junk. The junk is what's called big O of delta x squared. What that means is that these are terms of order, so with delta x squared, delta x cubed, or higher. Right, that's how. Very exciting, these higher order terms. Okay, so this is the only algebra that we need to do, and now we just need to combine it together to get our result. So now I'm going to just carry out the cancellations that we need. So here we go. We have delta f over delta x, which remember was 1 over delta x times this, which is this, times, now this is x to the n plus n x to the n minus 1 delta x, plus this junk term, minus x to the n. All right, so that's what we have so far based on our previous calculations. Now I'm going to do the main cancellation, which is this. All right? So that's 1 over delta x times n x to the n minus 1 delta x plus this term here. And now I can divide in by delta x. So I get n x to the n minus 1 plus, now it's O of delta x. There's at least one factor of delta x, not two factors of delta x, because I have to cancel one of them. And now I can just take the limit. In the limit, this term is going to be 0. That's why I called it junk originally, because it disappears. And in math, junk is something that goes away. So this tends to, as delta x goes to 0, n x to the n minus 1. And so what I've shown you is that d by dx of x to the n minus, n is equal to n x to the n minus 1. So now this is going to be super important to you, right on your problem set in every possible way. And I want to tell you one thing, one way in which it's very important, and one way that extends it immediately. So this thing extends to polynomials. We get quite a lot out of this one calculation. Namely, if I take d by dx of something like x cubed plus 5x to the 10th power, that's going to be equal to 3x squared. That's applying this rule to x cubed. And then here I'll get 5 times 10, so 50, x to the 9th. So this is the type of thing that we get out of it. And we're going to make more hay with that next time. Question? Yes. Question. I turned myself off. Yes.
Delta x.
The question was, the binomial theorem only works when delta x goes to 0. No, the binomial theorem is a general formula which also specifies exactly what the junk is. It's very much more detailed. But we only needed this part. We didn't care what all these crazy terms were. It's junk for our purposes now because we don't happen to need any more than those first two terms. Yes, because the delta x goes to 0. Okay, see you next time.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so I'd like to begin the second lecture by reminding you what we did last time. So last time, we defined the derivative as a slope of a tangent line. So that was our geometric point of view. And we also did a couple of computations. We worked out that the derivative of 1 over x was minus 1 over x squared. And we also computed the derivative of x to the nth power for n equals 1, 2, etc. And that turned out to be nx to the n minus 1. So that's what we did last time. And today, I want to finish up with other points of view on what a derivative is. So this is extremely important. It's almost the most important thing I'll be saying in the class, but you'll have to think about it again when you start over and start using calculus in the real world. So again, we're talking about what is a derivative. And this is just a continuation of last time. So as I said last time, we talked about geometric interpretations. And today, what we're going to talk about is rate of change as an interpretation of the derivative. So remember, we drew graphs of functions, y equals f of x, and we kept track of the change in x, and here the change in y, let's say. And then, from this new point of view, a rate of change, keeping track of the rate of change of x and the rate of change of y, it's the relative rate of change we're interested in, and that's delta y over delta x. And that has another interpretation. This is the average change. Now, usually we would think of that if x were measuring time, and so the average, and that's when this becomes a rate, and the average is over the time interval delta. Interpretation, this is the average change. Now, usually we would think of that if x were measuring time, and so the average, and that's when this becomes a rate, and the average is over the time interval delta x. And then the limiting value is denoted dy dx, and that is so this one is the average rate of change, and this one is the instantaneous rate. Okay, so that's the point of view that I'd like to discuss now and give you just a couple of examples. So let's see. Well, first of all, so maybe some examples from physics here. So Q is usually the name for a charge. And then dq dt is what's known as current. So that's one physical example. A second example, which is probably the most tangible one, is we could denote the letter S by distance, and then the rate of change is what we call speed. So those are the two typical examples, and I want to illustrate the second example in a little bit more detail, because I think it's important to have some visceral sense of this notion of instantaneous speed. And I get to use the example of this very building to do that. Probably you know, or maybe you don't, that on Halloween there's an event that takes place in this building, or really from the top of this building, which is called the Pumpkin Drop. So let's illustrate this idea of rate of change with the pumpkin drop. So what happens is this building, well, let's see, here's the building. And here's the dot, that's the beautiful grass out on this side of the building, okay? And then there's some people up here and very small objects. Well, they're not that small when you're close to them, that get dumped over the side there, and they fall down. That's, you know, everything at MIT, or a lot of things at MIT, are physics experiments. So that's the pumpkin drop. So roughly speaking, actually, the building's about 300 feet high. We're down here on the first usable floor, and so we're going to use, instead of 300 feet, just for convenience purposes, we'll use 80 meters, because that makes the numbers come out simply. Okay, so we have the height, which starts out at 80 meters at time 0, and then the acceleration due to gravity gives you this formula for h. This is the height. So at time t equals 0, we're up at the top. H is 80 meters. So this is the units here are meters. And at time t equals 4, you notice 5 times 4 squared is 80. So I picked these numbers conveniently so that we're down at the bottom. Okay, so this notion of average change here, so the average change, or the average speed here, maybe we'll call it the average speed, since that's over this time that it takes for the pumpkin to drop, is going to be the change in h divided by the change in t, which is, it starts out at, what does it start out as? It starts out as 80, right? And it ends at 0. So actually, we have to do it backwards. We have to take 0 minus 80, because the first value is the final position, and the second value is the initial position. And that's divided by 4 minus 0, time 4 seconds minus time 0 seconds. And so that, of course, is minus 20 meters per second. So the average speed of this guy is 20 meters a second. Now, so why did I pick this example? Because, of course, the average, although interesting, is not really what anybody cares about who actually goes to the event. All we really care about is the instantaneous speed when it hits the pavement. And so that's can be calculated at the bottom. So what's the instantaneous speed? That's the derivative. Or maybe I should, to be consistent with the notation I've been using so far, that's d by dt of h. All right? So that's d by dt of h. Now remember, we have formulas for these things. We can differentiate this function now. We did that yesterday. So we're going to take the rate of change, and if you take a look at it, it's just the rate of change of 80 is 0, minus the rate of change for this minus 5t squared, that's minus 10t. All right? So that's using the fact that d by dt of 80 is equal to 0, and d by dt of t squared is equal to 2t. The special case, well, I'm cheating here, but there's a special case that's obvious. I didn't throw it in over here. Last time, we define the derivative as a slope of a tangent line So that was our geometric point of view. And we also did a couple of computations. We worked out that the derivative of 1 over x was minus 1 over x squared. And we also computed the derivative of x to the nth power for n equals 1, 2, etc. And that turned out to be nx to the n minus 1. So that's what we did last time. And today, I want to finish up with other points of view on what a derivative is. So this is extremely important. It's almost the most important thing I'll be saying in the class, but you'll have to think about it again when you start over and start using calculus in the real world. So again, we're talking about what is a derivative. And this is just a continuation of last time. So as I said last time, we talked about geometric interpretations. And today, what we're going to talk about is rate of change as an interpretation of the derivative. So remember, we drew graphs of functions, y equals f of x, and we kept track of the change in x, and here the change in y, let's say. And then, from this new point of view, a rate of change, keeping track of the rate of change of x and the rate of change of y, it's the relative rate of change we're interested in, and that's delta y over delta x. And that has another interpretation. This is the average change. Now, usually we would think of that if x were measuring time, and so the average, and that's when this becomes a rate. And the average is over the time interval delta x. And then the limiting value is denoted dy dx. And that is so this one is the average rate of change, and this one is the instantaneous rate. Okay, so that's the point of view that I'd like to discuss now and give you just a couple of examples. So let's see. Well, first of all, so maybe some examples from physics here. So Q is usually the name for a charge. And then dq dt is what's known as current. So that's one physical example. A second example, which is probably the most tangible one, is we could denote the letter S by distance, and then the rate of change is what we call speed. So those are the two typical examples, and I want to illustrate the second example in a little bit more detail. because I think it's important to have some visceral sense of this notion of instantaneous speed. And I get to use the example of this very building to do that. Probably you know, or maybe you don't, that on Halloween there's an event that takes place in this building, or really from the top of this building, which is called the pumpkin drop. So let's illustrate this idea of rate of change with the pumpkin drop. So what happens is this building, well, let's see, here's the building. And here's the dot, that's the beautiful grass out on this side of the building, okay? And then there's some people up here and very small objects. Well, they're not that small when you're close to them, that get dumped over the side there, and they fall down. That's, you know, everything at MIT, or a lot of things at MIT, are physics experiments. So that's the pumpkin drop. So roughly speaking, actually, the building's about 300 feet high. We're down here on the first usable floor, and so we're going to use, instead of 300 feet, just for convenience purposes, we'll use 80 meters, because that makes the numbers come out simply. Okay, so we have the height, which starts out at 80 meters at time 0, and then the acceleration due to gravity gives you this formula for h. This is the height. So at time t equals 0, we're up at the top. H is 80 meters. So this is the units here are meters. And at time t equals 4, you notice 5 times 4 squared is 80. So I picked these numbers conveniently so that we're down at the bottom. Okay, so this notion of average change here, so the average change, or the average speed here, maybe we'll call it the average speed, since that's over this time that it takes for the pumpkin to drop, is going to be the change in h divided by the change in t, which is, it starts out at, what does it start out as? It starts out as 80, right? And it ends at 0. So actually, we have to do it backwards. We have to take 0 minus 80, because the first value is the final position, and the second value is the initial position. And that's divided by 4 minus 0, time 4 seconds minus time 0 seconds. And so that, of course, is minus 20 meters per second. So the average speed of this guy is 20 meters a second. Now, so why did I pick this example? Because, of course, the average, although interesting, is not really what anybody cares about who actually goes to the event. All we really care about is the instantaneous speed when it hits the pavement. And so that's can be calculated at the bottom. So what's the instantaneous speed? That's the derivative. Or maybe I should, to be consistent with the notation I've been using so far, that's d by dt of h. All right? So that's d by dt of h. Now remember, we have formulas for these things. We can differentiate this function now. We did that yesterday. So we're going to take the rate of change, and if you take a look at it, it's just the rate of change of 80 is 0, minus the rate of change for this minus 5t squared, that's minus 10t. All right? So that's using the fact that d by dt of 80 is equal to 0. and d by dt of t squared is equal to 2t. The special case, well, I'm cheating here, but there's a special case that's obvious. I didn't throw it in over here. The case n equals 2 is that second case there, but the case n equals 0 also works, right? Because that's constants, the derivative of a constant is 0, and then the factor n there is 0, and that's consistent. And actually, if you look at the formula above it, you'll see that it's the case n equals minus 1. So we'll get a larger pattern soon enough with the powers. Okay, anyway, back over here, we have our rate of change, and this is what it is. And at the bottom, at the point of impact, we have t is equal to 4, and so h prime, which is the derivative, is equal to minus 40 meters per second. So twice as fast as the average speed here. And if you need to convert that, that's about 90 miles an hour, which is why the police are there at midnight on Halloween to make sure you're all safe, and also why when you come you have to be prepared to clean up afterwards. So anyway, that's what happens. It's 90 miles an hour. It's actually, the building's a little taller, but there's air resistance, and I'm sure you can do a much more thorough study of this example. All right, so now I want to give you a couple of more examples, because time is, and these kinds of parameters and variables are not the only ones that are important for calculus. If it were only this kind of physics that was involved, then this would be a much more specialized subject than it is. And so I want to give you a couple of examples that don't involve time as a variable. So the third example I'll give here is the letter T often denotes temperature. And then dt dx would be what is known as the temperature gradient, which we really care about a lot when we're predicting the weather, because it's that temperature difference that causes airflows and causes things to change. And then there's another theme which is throughout the sciences and engineering, which I'm going to talk about under the heading of sensitivity of measurements. So let me explain this. I don't want to belabor it, because I just am doing this in order to introduce you to the ideas on your problem set, which are the first case of this. So on problem set 1, you have an example which is based on a simplified model of GPS, sort of the flat Earth model. And in that situation, well, if the Earth is flat, it's just a horizontal line like this. And then you have a satellite, which is over here, preferably above the Earth. And the satellite knows exactly, or the system knows exactly where the point directly below the satellite is. So this point is treated as known. And I'm sitting here, okay, with my little GPS device, and I want to know where I am. And the way I locate where I am is I communicate with this satellite by radio signals, and I can measure this distance here, which is called h. And then the system will compute this horizontal distance, which is L. So in other words, what's measured, so h measured by radio waves and a clock, or various clocks. And then L is deduced from H. And what's critical in all of these systems is that you don't know H exactly. There's an error in H, which will denote delta H. There's some degree of uncertainty. The main uncertainty in GPS is from the ionosphere, but there are lots of corrections that are made of all kinds. And also, if you're inside a building, it's a problem to measure it. But it's an extremely important issue, as I'll explain in a second. So the idea is we then get to the get at delta L is estimated by considering this ratio, delta L over delta H, which is going to be approximately the same as the derivative of L with respect to H. So this is the thing that's easy because, of course, it's calculus, right? Calculus is the easy part, and that allows us to deduce something about the real world that's close by over here. So the reason why you should care about this quite a bit is that it's used all the time to land airplanes. And so you really do care that they actually know to within a few feet or even closer where your plane is and how high up it is and so forth. All right. So that's it for the general introduction to what a derivative is. I'm sure you'll be getting used to this in a lot of different contexts throughout the course. And now we have to get back down to some rigorous details. Okay? Is everybody happy with what we've got so far? Yeah?
The equation for height.
Good question. The question was, how did I get this equation for height? I just made it up because it's the formula from physics that you will learn when you take 801. And it has to do with the fact that in fact, it has to do with the fact that this is speed, if you differentiate another time, you get acceleration. And this is the acceleration due to gravity is 10 meters per second, which happens to be the second derivative of this. But anyway, I just pulled it out of a hat from your physics class. So you can just say C801. All right, other questions? All right, so let's go on now. Now I have to be a little bit more systematic about limits. And so let's do that now.
The following content is provided under a Creative Commons license. Your support.
Any problems with this type? So it's a pretty fun game. I think I'm pretty lucky at it. The biggest one I've lost was in Hong Kong. I once had to pay around 1,200 USD. It was a pretty big table. But overall, I'm pretty good at this game. It's a game of skill for sure. So, all right. So, but sometimes this results in some funny stories with non-poker players. So this is something that happened to some poker players. So Poker Pro Matt, he goes to dinner with Poker Pro Steven, and then Matt brings Emily, who's a close friend who he also has romantic interest in. So when the bill comes, Matt's like, okay, I'm going to pay for Emily. So he puts in 2 credit cards. He's like, this second credit card is for Steven, is for Emily. And then Steven pays for himself, so Steven puts in 1 credit card. So they play credit card roulette. And then Matt, being a very lucky guy, pulls out both of his credit cards before Steven's, and Steven ends up paying for all 3 of them. Okay, so now the question is, who should Emily thank? So who would you thank if you were in Emily's shoes? Matt. Does anyone want to say thanks, Steven? Okay, because Steven actually paid for the meal, right? So I think it's a totally reasonable thing to do as a reasonable person to thank Steven, who actually had to follow his wallet. So in this class, we want everyone to think in terms of expected results and not actual results. So Emily should be thanking Matt. Because on average, Matt put in the card for Emily. And on average, Matt is going to be paying for Emily. Because Matt's going to be paying the 1/3 of the time that Emily would be paying. But at the time, Emily thanked Steven for her meal and then didn't say anything to Matt. And then Matt was upset about it and then told the entire poker community. And that's all I found out about this story. Okay, so we want to think about in terms of, on average, what your decision would have made, whether you would have made money in expectation or on average. So roughly, the law of large numbers says, over your lifetime, the amount you end up paying from credit card roulette is the same as you would have paid from splitting the bill. So, why split the bill? You might as well just save a lot of time by playing this fun game every single time. And over your lifetime, the amount you pay in credit card roulette is roughly going to be what you would have paid from splitting. And so all randomness eventually averages out to its expected value. That's what this is saying. So what does eventually mean? So basically, when we say a gamble is very risky, I'm not mathematically defining anything here, but I just want to throw out some intuitive concepts. So a risky gamble is a gamble where it takes a long time to converge at your expectation. But the point is, no matter how risky it is, eventually it'll get you. So poker players, so there's a saying that death, taxes are the 2 things that eventually get you. As poker players, we like to think that 3 things eventually get you. It's death, taxes, and the law of large numbers. Well, eventually, you're going to reach your long run. Okay, so here's another hypothetical situation. So let's say you get off at the wrong bus stop because you were distracted. And then you're upset yourself. You analyze how to not get distracted in the future and get off at the right bus stop. But then, after you get off at the wrong bus stop, you find $1,000 on the ground. And then you're no longer upset and you marvel at your riches. So this is sort of an absurd story, but situations like this happen all the time in poker. You're going to make a bad decision, but bad decisions still get a good result 49% of the time. And if you make the right decision, you're still going to get a bad result 49% of the time. So it's very important to analyze your decisions without being biased by the actual outcome that occurred. So you really want to be obsessed with this self-improvement, analyzing your decisions. If you made $10,000 in a situation where you could have made $12,000, then that's not good enough. So I want everyone to think in terms of, what's the maximum you could have made and analyzing what's the best decision you could have possibly made in every situation. And sometimes it's hard, right? Because if the result is exactly correlated with the decision, then you can just go back and look at the result and know whether you made a good decision or not. But that's why learning poker can sometimes be very, very hard. Because you don't have immediate feedback. You're not sure whether the decision you made is what caused you to make that money, or you just got lucky. Okay, so with that being said, so now let's talk about some ways to reason about poker hands. So roughly there's 3 levels of reasoning in poker hands. So level 1 is my hand versus your hand. So but by this I mean you can see what your cards are, and you look into your opponent's eyes and you say, okay, I can tell your cards must be pocket kings or whatever. Your hand must be this other hand, and you play your hand exactly against your opponent's specific hand because you have a soul read on them. So, all right, so let's see an example of this. So we'll watch an episode of Poker After Dark here.
Raise to 1200.
The logo I played with.
I think you would call it the sandpaper.
Sure. Button raises, never anything.
Contrary to what Patrick might think, Jennifer has a real hand, and it just got better. She's flopped top set. Patrick flopped a pair of tens with a gut shot straight draw.
Bet 2,000.
Full house? I can't beat that.
I thought you had pocket kings. I was like,
I almost thought I had you.
what did you have?
Okay, so this is a sort of well-known poker trend from way back in the day. If you're a Jennifer Tillingham, I'm sorry if I'm making fun of her. But basically, right, so she put her opponent on a specific hand. She looked at Patrick Antonius and had a feeling that he had pocket kings for some strange reason. And then what happened was, so she has pocket jacks here, which is a really, really good hand. It's a full house. And she just checked the turn and checked the river instead of trying to get Patrick to put more money in because she was so certain Patrick had pocket kings. And, just mathematically speaking, out of all the possible combinations of cards you could have, to put your opponent specifically on pocket kings in this example is basically unfounded. So this gets to level 2 reasoning. So level 2 reasoning is my hand versus your range of hands, versus your probability distribution of hands. And another name for this is exploitative play. So let's look at the different hand, and I'm going to show you how to reason about this hand using level 2 exploitative reasoning. So, okay. So I'm not going to go through the whole hand, but this is actually a real hand I played in Macau about 5-6 years ago. So we get to the river, and I have ace 10 in this situation. So the pot is 21,000 roughly, and my opponent bets 8,000. Sorry, so the pot is 21,000 after my opponent bets 8,000. So basically, the pot was 13,000, and my opponent bet 8,000, making it 21,000. And I have to decide whether to call. With a pretty good hand, I have a pair of aces here. But I know my opponent is Rain Khan, who's a very tight player and doesn't really like bluffing. So I don't think he's really ever bluffing. If I'm beating him here, it's because he's betting a hand that he thinks is good, but is actually worse than mine, like ace 8, basically. So I model my opponent's range as ace-king through ace-8. I don't think he has something even stronger like pocket nines because he would have raised more earlier in the hand. But basically, okay, so let me run through this calculation sort of slowly for those of you seeing pot odds for the first time. So here basically, I want to think of it like this. The pot, which includes the 8,000 he just put out, is 21,000. We're considering calling for 8,000, so if we lose, if we call and he turns up ace-king, which is a better hand, then our net result from this decision is negative $8,000. If we win, we get our 8,000 back, as well as the 21,000 in the pot. So we make our net is plus 21,000. So therefore, our win to lose ratio needs to be at least 8,000 to 21,000 in order for calling to be positive expectancy. So, all right, so we'll do the exact calculation. I'll try to do it somewhat slowly to show an example of how to do this calculation. So essentially what I do is I count the combinations of, I count the combinations of each hand that exist. So ace king, there's ace king, there's 8 combinations because there's 2 aces remaining that I haven't seen, and there's 4 kings remaining. So it's 2 times 4, there's 8 combinations. Same with ace queen, ace jack, and ace 8. Ace 10 and ace 9, there's only 6 combinations each because I have a 10, which makes him having ace 10 less likely. And for ace 9, there's a 9 on the board. So ace 9 is also slightly less likely. So ace 10, we actually get half the pot. So I'm just going to roughly, I'm going to make that equivalent to us winning 3 of those times and us losing 3 of those times, which is equivalent in expectation. So basically, if you do this counting, there's 33 combinations that beat us. There's 11 combinations that we beat. And so our equity is basically our probability of winning, which is equivalently the fraction of the pot that we own. So our equity in this case is 25%. And the pot odds are 21 to 8. And then so we need basically 1 over 3.56. So 21 to 8 is 2.56 to 1. We need equity 1 over 3.56 to call, which is 28%, which we don't have, so I folded. Sorry. So unfortunately, this calculation is a bit ugly. You just have to do it a bunch of times and convince yourself that you're doing the right calculation. Basically, you got to remember to add 1 when you're converting the odds ratio to an equity. But it's but yeah, so it should be fairly simple math. But so in this case, I folded because I didn't have the desired equity. So is there any questions about that? That was maybe a bit confusing, but I don't know of a great way to sort of show the exact conversion from pot odds into equity. But I just want to point out that they're slightly different. Just one is a ratio of win to lose, and one is basically a fraction of win over all possible outcomes. So just don't get confused by this. That's all I'm saying. I'm going to sort of quickly interchange between the two throughout the course, and you should try to get in the habit of being able to quickly compute between the two. Okay. So this is an example of level 2 reasoning, and hand reading is about using your opponent's past actions and your knowledge of their tendencies to tweak your probability distribution over what you think their hand is. So hand reading is not about pegging your opponent on a specific hand. So, it's sort of a marketing message. Poker players, they wear sunglasses, they have earplugs to prevent people from reading their soul. I mean, it matters a bit, but really these things, things like I scratched my ear before I raised, it should affect your belief about my cards a very small amount, way less than what Lady Gaga and the media makes it seem like. Okay. So that's sort of how you reason about a hand exploitatively. You build a model for how your opponent behaves, and you make the decision that's the most positive expectancy against that model. And you can go very, very far with level 2 reasoning. You can basically build a career out of level 2 reasoning. And it's best targeted towards individual opponents with specific tendencies that you're trying to take advantage of. So, okay, so this sounds very good, right? This sounds like a great way to play poker. I figure out what my opponent's doing, right? I figure out the probability distribution and play in a way to make the most money from him. So, does anyone have any problems with this type of reasoning? So, okay, so I've got some $20 Amazon gift certificates from Acuna Capital. If someone can point out potentially something you don't like about this type of reasoning, I'll give you this gift certificate. Yeah.
You reveal a lot of information about what your hand is when you think like this.
Right, but what if your model incorporates the fact that they're going to behave based on what they think is in your hand? Yeah.
Well, I mean, it might take you a long time to build this model on the players being the table or whatever. You spend because before you have the model, you can't use this line of reasoning.
Right.
So it's expensive to
do it. Right, yeah, that's a good point. Yeah. So first of all, level 2 reasoning is not easy. Even though it has flaws, even playing very good level 2 poker is not easy. Building the model can be very hard, and you could be wrong. Yeah, but that's not really what I'm looking for. Yeah, Colin. Yeah.
Because if your opponent knows your reasoning, you could maybe bet a certain way to push it to 28%, where you would only call if it's.
Right. Okay. Yeah. Okay. I think that'll be good enough. Okay. I'm gonna give this to you. I'll give it to you at the end. Okay. Right. So essentially, yeah. The problem is so it's this assumption. The fatal flaw in every plan is the assumption that you know more than your enemy. Does anyone know where this is from? By the way, if you do, I'll have another $20 gift certificate. Does anyone know where this phrase is from? Yeah. Right.
From Clausewitz?
No. Yeah, okay.
The odds of war?
No. Okay, it's okay. If no one knows, I'll keep the certificate. Okay, no, it's okay. Alright, so essentially, the problem with this line of reasoning is your opponent does not play according to a fixed static algorithm. They're also an intelligent human who's taking this class, who's building models for you and adapting the strategy to beat you. Right? So if you assume your opponent plays with a fixed strategy, but what if they're doing the same for you? So now I'm going to get to the third level of reasoning, which I call optimal play. So let's analyze the exact same hand using level 3 reasoning. So don't get me wrong, level 2 reasoning is great. If you can do level 2 reasoning very well, you can make a ton of money. But level 3 reasoning is a completely different way to analyze this hand that can also make you a lot of money. So level 3 reasoning, I'm going to think like this. Instead of thinking, so level 3 is my range of hands over your range of hands. So instead of looking at my specific cards and figuring out what my cards are, I'm actually going to also put a probability distribution over myself and ask myself, to my opponent's eyes, what is the probability distribution of my hands? And in this specific spot, let's just say I decide that my range in this spot is ace-jack through ace-7. So not including ace-9. It's basically ace-jack, ace-10, ace-8, ace-7. So this is the way I do the calculation. So let's just assume I know my opponent's propensity is to bet 1 over 1.6% of the pot on the river. So roughly in this spot, so the pot was 13,000 on the river, and I know that my opponent's going to bet 8,000. So I must call with the frequency such that their EV from bluffing is 0. So that's essentially my goal with optimal play. So essentially what I'm saying is, let's say they have a really bad hand. They have like Jack 10 for Jack high, which is almost certainly going to lose the pot if they don't bet to try to get me to fold. Then I want to call with the frequency such that with those hands, regardless of whether they bluff, their expectation is 0. So how do I do that? I just make my call to fold ratio 1.6 to 1. In all these computations, to make it easier, I'm assuming I'm rough. 1.6 is like approximate for the ratio. It's actually 13 over 8, but I chose. It actually turned out to be mostly Fibonacci numbers, so the ratio is around 1.6 to 1 for all of them. So I'm making that shortcut. Okay, so my call to fold ratio needs to be 1.6 to 1, so that if they have a bad hand, their expectation from bluffing is 0. It doesn't matter whether they bluff. So if I do this calculation, then ace 10, sorry, there's a typo. Ace 10 is definitely in the top 61.5% of hands I can have, so I need to call. Okay, so I'm not building a probability model for them. What I'm essentially saying is, if I'm not calling ace 10 here, then they can exploit me by bluffing too much, and I'm just folding all my hands here, and they're going to be able to make money off of me. To prevent this, I must call ace 10, which is a 61.5 percentile hand in my range, so that they can't exploit me. So I'm going to make an analogy with RPS. So rock, paper, scissors. Does everyone know how to play this game? So you either throw rock, scissors, or paper. So there's no way to do it with this game. Right? I know people, if you grew up in a different background, you might call it something else, or you might have different rules. But the rules I play with is rock beats scissors, scissors beats paper, and paper beats rock. Okay, so exploitative play, you think like this. You say, since my opponent just played rock 3 times in a row, I think they're probably not going to play rock a 4th time in a row. So I'm going to play scissors because I know I can't beat beat. Optimal play just says, I'm going to memorize a sequence of random bits and always play each of rock, paper, and scissors with probability of third. So this is an analogy with rock, paper, scissors. And so one question I often get is, if when you play optimally, you're making all your opponent's decisions the same, then your opponent essentially is never making a mistake, because regardless of what they do, it's the same. Then how do you even make money playing optimally? So in rock, paper, scissors, that's true. If my strategy is just play rock, paper, scissors, each with probability of third, I'm never going to beat you more often than I should. But in poker, there's enough opportunities to essentially be inconsistent. For example, like sometimes you'll see players fold 7-6 suited, and then because later they're like bored and feel like playing a worse hand, they'll like call 6-5 suited in the exact same situation, which is like basically making a strictly dominated strategy, or like check raising a strictly inferior range. Essentially, the theoretical optimal strategy will still extract money slowly from even the best players, because even the best players in poker right now, there's going to be slight inconsistencies that are not theoretically optimal. So essentially, so the optimal strategy, another way to think about it is a Nash equilibrium, if you've heard of the term, because the best response to the optimal strategy is the optimal strategy itself, whereas the best response to any exploitative strategy is going to be a different strategy. Whenever you play an exploitative strategy, you stand to be beaten by a different exploitative strategy that re-exploits you. So this is the difference. Optimal play is you play each with the same probability. Optimal play, you're indifferent to your opponent's move. So optimal play, you're making a lot of money when your opponent does something strictly suboptimal, whereas in exploitative play, you make a lot of money when you're winning the mind games, and you lose a lot when you're losing them. So it's exploitative play is sort of like, I know that, you know that, I know that, you know that, I know this, but you know that, I know that, you know that, I know that, you know that, I know this. So basically, you get into these mind games, and if you're good at them, then it's pretty good, right? If you're playing rock, paper, scissors against a 4-year-old child, probably you don't want to play optimally. Probably you want to like look at their face and try to figure out what they're going to do and try to beat them, right? But if you're playing rock, paper, scissors against the rock, paper, scissors world champion, which there is one actually, then probably you just want to memorize a sequence of random bits and play each with a probability of third. So another good thing about exploitative play is it's intuitive. We sort of grow up thinking in terms of exploitative play, right? I think that's a fair statement. In most things, it's like, what do you think might happen? Okay, if that might happen, okay, I'll do this. But optimal play is sort of a weird mentality, because it's sort of like, I'm just gonna analyze what my opponent could potentially do. So you need an opponent essentially, and then I'm just gonna perform an action that sort of makes it so that my opponent can't really beat me. Okay. So that's enough about those two general concepts. I'm going to take a short break right here since it's a good time. So I'm going to continue, and we'll get into some actual poker. But first, okay, we're going to play one last game. So, okay, we're going to play a game called Who's Taller, okay? Anyone can join the contest for $1. Okay, we're not actually having this, so don't get out your wallets. Okay, basically, okay, so, and then the tallest person who joined the game gets the entire pot. So all the money, all the people who joined the game, we're going to measure who's the tallest, and then that person gets everyone's money. Okay, so let's play right now. So everyone close your eyes so that you can't look in here. Everyone close your eyes. No peeking. No peeking at how to... Okay, so I want everyone close your eyes. Is everyone's eyes closed? Okay, so put up your hand if you want to join the contest. Put it nice and high so that I can see. If you want to join the contest. Alright, so raise your hand highly. It's okay, there's no embarrassment. The whole point of poker is where... Okay, cool. So now everyone open your eyes. Okay, so I think 5 people joined. Okay, so hey, guys, come down here. Let's see who would have won. Let's see who would have won. Don't be shy if you joined. It's okay. It's totally okay if you lost. Okay, so I think the 4 of you. Okay, cool. Sorry, what's your name? Justin. Okay, Justin. Okay, so I think Justin would have won. So, all right, good job, Justin. You would have made $3 from this game. Okay. All right, cool. So, okay, what's the point of this game? The point of this game is, so from a game theoretic point of view, no one really should be playing this game. So this is only known as the K-Beauty game from game theory. So let's see. So how tall are you, Justin? 6'5". 6'5". Okay. So why did you play the game? because you thought there's probably someone who's going to be like 6'2" who might play the game, right? So, right, but if everyone knew that, you know, if you're only 6'2", you shouldn't be playing this game because someone might be 6'5", then you wouldn't play the game, right? Because someone else is only going to play the game if they were like 6'8" or something, right? So essentially, basically, once you so let's say we played this game again, probably only just to play. But eventually, this game always devolves to a situation where basically no one is willing to join, because you know that no matter, even if you're like 7 feet tall, you're LeBron James, you would know that someone would only play this game if they were the tallest person in the world, essentially. So basically, poker without blinds, which is the money that's put into the pot at the start of every hand, would essentially be like the twos taller game. So when you play poker, you want the motivation of every hand to be stealing the blinds, stealing the money that was forced into the pot without the choice of the person. So you would always fold king-king, which is the second best hand in poker pre-flop, if there were no blinds. So, okay, so suppose we were to play Who's Taller again, but I told you that I'm going to force Lee Marie to play. Okay? So now we've got a game. Because now, even if you're not sure whether you're the tallest person in the room, if you're taller than Lee Marie, then you have a chance of winning. So that's essentially why we need blinds to have a game. So basically, you want to think of so you always want to think of how many chips you have in terms of the blinds. And so having $400 in front of you in a game where the blinds are $1 or $2 for our purposes is equivalent to having $4,000 in front of you in a game where the blinds are $10 and $20. Because essentially everything you're wagering is relative to stealing the blinds that were forced into the game at the beginning. So in both of these situations, we say that you have 200 bets or 200 big blinds or 200 BB. Okay, so that's how to calculate your stack size. But what's actually important isn't stack size, it's effective stack size. So effective stack size takes into account the stack sizes of the people remaining in the pot as well. So now we've got a game, because now even if your drink is relative. To stealing the blinds that were forced into the game at the beginning. So in both of these situations, we say that you have 200 bets or 200 big blinds. Or 200 BB. Okay, so that's how to calculate your stack size. But what's actually important isn't stack size, it's effective stack size. So effective stack size takes into account the stack sizes of the people remaining in the pot as well. So, okay, so I'll give an example. So in this case, so we're the player with the ace-jack, and we decided to go all in. So what is our exact stack size? So the big blind is 2,000, the small blind is 1,000, and we wagered in total 42,000. So what's our stack size? 21, right? It's around 21. It's around 21 big blinds, but we didn't really risk 21 big blinds here, did we? Did someone? Okay, I'll give a $20 gift certificate. How much did we actually risk in some sense? Yeah.
I can't see it quite well, but I think 12 and a half big blinds.
Okay, yeah, exactly. Okay, cool. Okay, I'll remember it. I'll put it here. Okay, so we only risked 12 and a half big blinds because everyone in front of us has already folded, and the two players behind, the small blind and the big blind, one of them only has 7.5 big blinds, and the other one only has 12.5 big blinds. Can everyone see that? So even though, UTG plus 2 has 32.5 big blinds could have theoretically covered us, and we could have theoretically taken all our money. But on this hand, because they already folded, we're essentially only risking at most 12.5 big blinds. That's the most we can lose. So we can't be eliminated from the tournament with this hand. So here's another example. So here you see this guy that I'm going to call Low Jack for now. You see him go all in for 16 big blinds. So in this case, technically, he could lose all his money because we have more than 16 big blinds, and we do cover him. But, you know, in reality, I'd say he's probably not, on average, risking 16 big blinds because most of the people who could call him, other than us, have way less than 16 big blinds. Does that make sense? So essentially, there's not like an exact formula for effective stack size, but you want to sort of think of it in terms of, you look at the stack sizes of all the people who could potentially play the hand against you, and you want to look at, you know, roughly how much am I going to be risking in this hand. Okay. Okay, so that's effective stack size. That makes sense to everyone? Okay. Okay, so the second thing I want to talk about that's very important is position. So position is basically where you are at the table relative to the blinds. So how many players are remaining to compete versus me for the blinds? Essentially, the fewer players that are left, the less strong my hand needs to be to attack the blinds. So I'm going to give names for the positions. Basically, the thing that matters is how far you are from the button. So in this example with Ace-Jack, when everyone folded to you and you're the dealer, which is also known as the button, essentially to steal the blinds, you just need to get through the 2 blinds themselves. So that's essentially 2 players. And then, you know, if you were one position earlier, when it was folded to cutoff, then he had to deal with 3 players. So you want to name everything relative to the dealer, essentially. So we can just quickly go through the names. They'll get more familiar as time goes on. So the first person to act is, we call them under the gun. So that's this guy here. And then we go around the table. It's under the gun +1, under the gun +2. So there can be different names for the same position. So in this specific hand, where there were only 6 players at the table, you know, you could have called Low Jack under the gun, because under the gun is the first person to act to the left of the big blind. But essentially, it's more clear to say Low Jack, because when you say under the gun, you have to say under the gun at a 6-handed table, and then people will know, okay, that means you got to get through 5 hands. But if you say Low Jack, it's very clear. You have to get through 5 hands. So under the gun, and then +2, and then Low Jack. You can also call under the gun +2, Low Jack -1 if you want, and then Hijack, Cutoff, Button. Don't ask me where these names came from. I actually have no idea. Okay, and then Small Blind, Big Blind. So that's position. And the importance of position is basically the later you are, the fewer hands you got to get through to steal the buttons, to steal the blinds if everyone has already folded. Okay. So the third thing that matters in a poker hand is equity. So we talked about stack size, we talked about position. The last thing is actually your cards. So the equity of your cards is basically your secret height for the who's taller game. So you can think of it like that. Your cards is like your secret height. And the probability of you winning the pot, or equivalently the fraction of the pot you would win once the remaining cards are dealt, is called your equity. So I'm going to give some examples of calculating equity. So here's an example where we get it all in on the turn. And so I have 5-4 of spades here, so I'm not in a great position. But let's try to count how many outs I have. So does someone want to just name a river card that would help me win the pot? Yes. Right, 7 of spades. So that gives me a straight and a flush, actually. So let's go along those lines. So how many spades are there left in the deck? Yeah.
Should be 9 spades.
Right, 9 spades. And then how many cards help me make a straight here?
6 more.
Right, a 7 or a 2, right. So it's 6 more because there's 8 7s and 2s, but I'm double counting the 7 of spades and the 2 of spades. So that's 9 plus 6, and then I actually have to subtract 1 more card. Does anyone see what it is? Yeah.
Queen of spades.
Right, the Queen of Spades, because that's actually a disastrous situation, because then if it wasn't all in, I would probably put in more money on the river thinking I have a flush and lose to a full house. Right, so it's 14 outs, 17 minus 3, our equity is around 32%. It's 14 over the 44 cards that could still come. Okay, did that make sense to everyone? So that's one way of calculating equity. It's just a very simple probability distribution over the remaining cards in the deck that could come. And if you're worried, like, what if someone folded the Queen of Spades, so I shouldn't be counting that? Essentially, you just want to pretend that the cards that are in the muck, like the cards that were folded by other players, they're essentially irrelevant because they could have folded the Queen of Spades, but they could have also folded an irrelevant card like the Jack of Hearts or something. So essentially, you just want to, all the cards that you haven't seen, it's easier to just assume that they don't affect anything. I mean, in theory, they affect things a bit because if you know that the dealer button folded 2 cards, even if you don't know what they are, they're probably more likely to be really crappy cards like 2s and 3s rather than aces, because if they had an ace, they would have played it. But I think not worrying about that is fine. You don't need to worry about it. Okay, another example of equity calculation. So it's the exact same example as before, but in this case, the probability distribution isn't over cards that could come. All the cards have already come. The probability distribution is just over my opponent's hand. So, this is the same calculation. We calculated our equity is 25%, and that's not a probability distribution over cards to come. That's a probability distribution over our beliefs of our opponent's hand. Okay, so example 3 of calculating equity. So this one you can't really do by hand. It's, so let's say you get it all in pre-flop with ace-king suited against pocket 2s. And you basically need a calculator. There's certain websites that help you do this. And ace-king suited against pocket 2s, if they don't have a 2 of your suit, is actually a very small favorite, which is kind of cool. But if they have the 2 of hearts, then you're actually a slight underdog. Okay. So just make sure for all the different things equity could mean. Equity could mean a probability over river cards, probability over the unknown. A very good calculator in general is PokerStove, which I'll have lots of examples of in my slides, and you can download it via this link here. Right, so this is an example of using PokerStove. So, you can put in exact calculations. Like, let's say you get it in with 2 of diamonds, 2 of spades, so pocket 2s on a flop of 5, 3, 2, versus a range where your opponent is going to have a big pair, like pocket jacks plus. You can actually run it, and your equity is 85%, which is actually surprisingly low, I think. Because it seems like, you've got 3 of a kind. They've only got a pair. They have 2 chances to hit 1 of 2 cards, but there's a lot of random stuff that can happen, like if they have aces, they can make a straight, they can make a backdoor flush, the board could come 2 more 5s, which counterfeits their 3 of a kind deuces. So this is another example of calculating equity. Right, so this is just a summary of the different situations you might want to calculate equity. And yeah, I recommend you download PokerStove, but you don't really have to. And I guess one question you could ask is, how do you actually do this at a table? So essentially, you just have to, if you do this a lot while you're studying about hands and thinking about poker, eventually I've been able to just memorize a lot of situations in general, what the probabilities are, or at least what the correct decision is. Okay, so now let's talk about raising to win the blinds and antes. Okay, so the antes, an ante is an extra small bet that each player must put into the pot each hand, and these sum to around a big blind. And they come in during the later stages of the tournament, and they're inexistent in cash games. So I sort of swept this under the rug in the earlier examples.
Unbelievable. Just crushed.
So in let me go back. So like in here, do you see the 1200 in the middle? So I actually sort of stuck this under the rug, but that comes from each player being forced to put in 200, which is 1/10 of the big blind, at the start of every hand. And if you're playing tournaments, then this will usually be the case. Antes will come in fairly soon. If you're playing cash games, where you just sit down and you can leave whenever, and you sit down and you just play for your own play money, then there's usually no antes. But antes actually make a world of difference in terms of what you want to do. So it's not just the stakes are bigger when there's antes. Because you don't want to just think of it like there's extra money in the pot every hand, it's equivalent to the blinds being bigger. That's not true, because you also have to put in an ante. So if the blinds were proportionally bigger to cover the antes, you would have to raise to a bigger size to try to steal the blinds. But with antes, you don't need to raise to any bigger size to try to steal the blinds. So it's actually very action driving. It's very exciting. It makes it so that you want to play a very wide range of hands, and you really just want to be trying to win the blinds as often as possible, because winning one pot with the antes is so big. Okay, so this is what it looks like. Alright, so the first thing I'm going to say is, if you're going to start playing tournaments tonight, is if no one has raised yet, you don't want to call. You want to raise to give yourself a chance of winning the blinds without seeing a flop. So I'd say the most common beginner mistake I see beginner poker players make is not raising when no one has raised before. So in this case, it would be just calling for 2,000 and trying to see a flop. But the main issue is you're giving the big blind, they can just check and see the flop for free. Whereas if you raise, you put them to a decision and they might fold, and you might just win the pot for free without having to do anything, essentially. So how much do you raise? When I say raise, so the minimum raise size you can do is raising to 2 big blinds. However, this is a bit small because you give the blinds fairly good odds to make a profitable call, although it's not even that bad. So let me just talk a bit in general about raising big versus raising small. So the advantage of raising small is that you're risking less. Like, let's say you raise and then the next person re-raises and then the next person goes all in, right? So probably those 2 people have pretty good hands and you want to fold. If you raise to a small size, then you can fold and you don't lose that much. If I raise to like 5 big blinds, then I'm losing a lot more. But what's the benefit of raising big is you give other people worse odds to call. If I only raise to 2 big blinds, let's actually do this calculation. Let's say here, instead of going all in, I raise to 2 big blinds, which is 4,000, right? What odds am I essentially giving the big blind to call? So think about it as, so this is actually in this very exact situation, this is a very common mistake I see beginners make, which is you raise to only 4,000. Yeah.
So there's 8,000 in the pot and they have to call 2,000, so it's 41?
Right. So it's 41, but there's also the small blind. So there's actually going to be 9,000 essentially in the pot.
Is it?
Yeah, so it's going to be 8,800. Yeah. It's going to be 8,800, so approximately 9,000, and they only have to call 2,000 to see the flop. Does that make sense to everyone? So the odds are actually 4.5 to 1. And ace jack offsuit is a great hand, but there's no hand that ace jack offsuit is more than a 4.5 to 1 favorite against. So in some sense, it's basically, even if they have jack 2 or whatever, ace 2, think of the best possible case for you. You're still not doing better than the odds you're giving them. Okay, so on the other hand, though, you really don't want to. It is really risky to raise more than 2.25. So a reasonable rule of thumb, I'd say, is to raise to 2.25 big blinds in tournaments. I know it's pretty close to do. If you just raise to 2, it's probably not that bad. But roughly speaking, I think this is a reasonable rule of thumb. Earlier, you could try to raise to more. I think that's sort of customary, although I don't think it's theoretically optimal. You'll often see players raise to like 3 big blinds, especially when you watch like pro players. They'll raise to bigger, but the main reason is because they're the better player by a lot, and they're just trying to make big pots, which is reasonable. If you think if you're trying to just play big pots and win big pots, then raising to a bigger size is fine. But I don't think there's any theoretical reason to raise to more than 2.25 big blinds in most situations. Other than when, like in cash games where all players have a lot of money, then it's a bit different, because also in cash games you're not worried about risking more because you're not worried about losing out of the tournament. But okay, so the other thing is, instead of raising, you should just go all in if the effective stack size is 12 big blinds or less. So recall, the rationale for raising big is to prevent others from calling for cheap, but the rationale for raising small is to lose less if we get re-raised and have to fold. But 12 big blinds is sort of the point where it's small enough that you never really want to fold after committing 2.25 big blinds. So if I only have 12 big blinds, I raise 2.25, I've only got 9.75 left after. Even if I get, if I get raised and re-raised, maybe I'll fold. But even if I get re-raised once, if I'm raising in the first place, my hand is going to be reasonable. Like if for the who's taller game, I'm not going to raise in the first place if I'm like 5 feet or something. So your hand will be reasonable. So this is sort of beginner mistake number 2, is being too scared to go all in pre-flop. So that's why this ace-jack hand, I actually cheated a bit. So technically here the effective stack size is, the big blind has 12.5 big blinds, but the small blind only has 7.5. So I roughly said the effective stack size is less than 12, and I just went all in. So that's definitely beginner mistake number 2 in tournaments, is to be too scared to go all in pre-flop. So what your goal essentially should be, I should say the rule is, so all of the numbers I said assume there's antes. If there's no antes, you should change it to 10 big blinds. So the threshold for going all in should be less, because when there's no antes, you want to be risking less, because the pot is smaller. Okay, so overall, when I talked about position, I talked about stack size. Essentially, what I'm trying to get the point across is, if you're just starting out, players tend to make all decisions based on their cards. It's just, I have a pair of jacks, I see my pair of jacks on this board, I have a pair that's pretty good, and you sort of tend to ignore what the effective stack size is, how much you're wagering, and position. But experienced players, the cards actually matter much, much less to them. In fact, if you're doing optimal play, you don't even care in some sense what your cards are, you just care what your range of cards are at that point. So experienced players, they're willing to raise the blinds with much weaker hands from good positions rather than early positions, and they're going to risk going all in a lot more frequently with a lot worse hands if their stack size is low. So I want you to think about that. So if you're just starting out, that's fine. If you're still trying to figure out whether you have a straight and stuff like that, that's fine, and it's totally fine if you try to play based just on your cards, but I want everyone's goal by the end of the class to be able to play based on these other factors more so than your cards. Okay, so that being said, I'm going to give you some concrete suggestions for those of you who might want to start playing tonight of what hands you should be playing from each position. And so here, most of the tournaments will have 9 players per table, and so this is going to be roughly a range I recommend to open. So these are the range of hands you should be playing from the worst position, so under the gun at a 9-handed table. So there's 8 players left behind you who could pick up really good hands. So it's aces, kings, queens, jacks, ace king suited, ace king offsuit, tens, ace queen suited, ace queen off. So that's basically the list of hands. So this is these are only premium hands, right? This is like 6.2% of hands, I think. It's a very premium range. So note how tight this is. Because the thing to remember is only the best hand out of 9 hands at the table is going to get the pot. When there's 9 hands, even though the average hand is really bad, the best hand out of 9 hands is always going to be pretty good. So to even think that you have a chance, you need to start out with a very premium holder. So roughly what do you add as you go around the table? So for the second position, I'm going to post all these slides before the tournament start, by the way, so you don't need to feel you scramble to write all this down. I'm going to post it. So this is from the second position. I put in black the hands that I would open from the previous position, and I put in red the hands that I would open from that position in addition. So second position, there's one less player. Okay, I'll gamble with sevens, ace jack, king queen, ace 10 suited. So we'll get it on the table, and then the range will slowly increase. Also note that these are very conservative ranges. If you watch like high stakes poker, probably the players will open a lot more hands than what I'm recommending here. But my general experience has been, when you're just starting out to play poker, it's much easier to err on the side of being too tight than being too loose. So, because it's in some sense a lot easier to play pocket aces than 7-5 suited. With pocket aces, you're always going to have a pair of aces, or better, you just bet. And then with 7-5 suited, you need to be able to bluff very carefully. You need to sometimes be able to try to get value when you just hit a pair of sevens, and it's just a lot harder. So the ranges I'm suggesting are very tight by most poker standards. By tight, I mean conservative, but I think that's the right side to err on when you're just starting. So these are the range. Okay, so now we're going to get as we get to the later positions, so this is low jack, we're opening more hands now. Any two suited broadways, so that's hands like Jack 10 suited, Queen 10 suited. It's basically any two cards that are the same suit and both 10 or higher. So maybe I should just run through this quickly. So why is having your cards be suited good?
You get the flush.
Right. So if it's suited, you're more likely to make a flush. But if you have two unsuited cards, then there's two different flushes. Right? So, okay. Like if you have queen of diamonds, 10 of spades, then you can make a diamond flush or a spade flush. But essentially that argument is wrong because there's two reasons why it's wrong. One is it's not more likely because you need 4 of the suit to make the flush. And 2 is when you make the flush, it's also more obvious you have the flush. Like if you only have 1 diamond, even if it's the ace of diamonds, once there's 4 diamonds on the board, it's way more likely that you have a flush, so you're going to get paid off less. Whereas if you have 2 diamonds in your hand and there's only 3 diamonds on the board, it's less susceptible that you have a flush. Okay, so hijack is 3 to the button. So this is what I would recommend. Okay, so any pair. So pairs are pretty good. Any suited ace. So suited ace means any card with any hand with an ace and another card of the same suit. Any suited connector. By that I mean hands like basically 2 cards that are next to each other and also the same suit, like 10, 9, 10 of spades, 9 of spades, or any 2 unsuited Broadway cards. So I do use a lot of terminology here, so yeah, please stop me if something is unclear. You can Google most of these, I think, but okay. So yeah, and suited connectors are good. So like a hand like 7-6 suited is often better than a hand like 10-6 suited, even though the 10 is bigger than the 6, because 10 is sort of a small enough card where it's not that relevant, the fact that it's a big card, but the fact that 7-6 is connected and can hit a lot more straights is very relevant. Okay, so for cutoff, I'm just going to show you on Poker Stove because there's sort of too many to list. But the thing I want you to note is the percentage. It's 30%, right? So remember, under the gun, I recommended playing 6%. So we've multiplied how bad our hand could be for us to play by 5. And I think this is what I really want you to try to do. And I think what a lot of new players don't do enough is they always play the same cards regardless of their position. And then even crazier, on the button, if everyone in front of you folds, I recommend playing about 55% of hands. You know, this is huge. I want you to play Jack 3 suited. Who thinks Jack 3 suited is a good hand? Or King 4 offsuit, or Queen 6 offsuit. Okay. So now what hands do you play from the small blind if it's folded to you? So let's compare opening from the small blind to opening from the button. So for small blind, it's a bit different now. So I should mention this because when you're raising from the button, from the dealer, if you get called, you get to act last post-flop. So I'm going to talk more about this in future lectures, but this is basically called having position post-flop, and having position is basically good.
For all these hands, are you assuming that everyone's folded behind you?
Yes. If people haven't folded, essentially, I'll talk more about this in future classes, but essentially what you need to do like let's say this guy raised and you're the button, right?
Yeah.
Essentially, you need to consider what his range is and calculate your equity against his range, which you can do.
Completely different.
Right. So the calculation is essentially completely different. So essentially, the first guy who raised sort of just determines sort of what the barrier to entry to the pot is. Because essentially, the first guy that raises is if it's from under the gun. You know, he's telling you my range is pocket 8s plus. Even if he's sort of loose, it's still going to be like pocket 4s plus and like Queen 10 suited plus. Basically, it's saying if you're playing 8-6 suited, then you're basically an idiot because my range is way better than that. So essentially the first guy who plays this hand sort of sets the tone on how good your hand needs to be. Thanks for that question. Yeah. So I'll talk more about this in a future lecture, but essentially, essentially that's what you need to do. Okay, so from the small blind, let's compare opening the small blind from opening the button. So the issue with opening the small blind is if the big blind calls, you actually don't have position post-flop. The big blind gets to act after you post-flop. So it's actually a lot worse in some sense than opening from the button, because you don't get to act last. But it is better in the sense that there's one fewer person you get through, and also you have less to wager, which is actually really relevant. Because from the button, you know, if the blinds are if the blinds are 2,000 or 1,000, or okay, let's just take this. If the blinds are 20/40, if you want to steal the blinds from the button and you want to do 2.25, you need to put in 90, right? You need to raise to 90 and you need to wager 90. But if you're raising from the small blind, you only need to put in 70 more. So you're actually paying a smaller price to try to steal the blinds. But the fact that you're out of position is a very important negative. So I'd say all these factors balance out, and you can roughly play the same range of hands from the small blind as you would from the big blind. I think that's a reasonable rule of thumb. But the fact that you're out of position hurts a lot less as stacks get shallower, essentially as effective stack sizes get a lot smaller. So it's so you know, you could really drastically increase this range if you only have like 10 big blinds from the small blind.
I agree. I kind of want to short this.
Okay. All right, so let me just give a few caveats about this. Okay, so actually, I'll leave it to you guys. Okay, if someone comes up with a very good complaint about these recommendations I'm giving you, I'll give out the last $20 gift card. Okay, so what are some problems, sort of? Okay, so I mean, normally I get lots of complaints in this section. You already got one, but you can answer. Yeah.
You're very predictable, so.
Right. Okay. Right, good. That's a very good point. So a lot of people ask me, you know, why would you follow these? If I follow these, everyone knows what I'm doing. Well, the point is, for most of these, even this range, right, it sort of encompasses enough hands. So this is where I'm talking about optimal balanced play. I think, you know, even though humans haven't solved poker, I think roughly, if you want to ask, you know, I would guess that roughly the optimal range of hands to open from this position is something like this. It's going to be looser, but it's something roughly like this. You know, probably you want to probabilistically play some smaller cards just so when the flop comes 2-2-4, you can potentially have a 2. But essentially, you're not doing bad here, because if the flop comes 3 small cards, then you're going to be doing pretty well with all your big pairs. And if the flop comes big cards, you still got ace king, ace queen, ace jack in your range. So yeah, but that is a correct, you know, that is a good complaint. And if you so you know, in theory, it's in theory optimal to play 7-7 some fraction of the time, 6-6 some fraction of the time, and like 2-2 some fraction of the time. But that's sort of making things really complicated. And you know, if I don't want to add 2-2 to the list, because if you play 2-2 every single time, then that's way too loose. You're just spewing money by raising with 2-2 against this many players behind. But you know, so ideally, maybe with 2-2, you should do a random number generator and 10% of the time play 2-2. That would probably be theoretically optimal. Okay, good. That would have gotten this, but okay, I'll give it to yeah.
I think another problem with playing really tight all the time is that you are also very easily bullied around the table. Right? So if someone bets and you know you really want to play, you really want to stick to your tight range, you'll fold and you'll maybe miss out on something that you shouldn't have, depending on your position and things.
Right.
Like
Okay.
that.
Okay. Good. Yeah. So these are pretty tight in that, you know, it does give the other people incentive to raise a lot, because everyone's going to be folding a lot because they're just waiting for these really good hands. Okay. Okay. Yeah. That's good. So, okay. Are there any other questions about these suggestions I gave you guys, or other potential complaints? I'm going to give this gift certificate to you unless someone thinks they have another complaint. Okay. Okay. So I'll give this to you at the end. Okay, so, all right, so this is one thing that I didn't really address. So I talked about going all in as well as just raising. So how do these ranges differ? The answer essentially is they don't really differ. So, you know, let's say, you know, here these are the hands I told you to play, right? Let's say you're sort of small enough, you only have 12 big blinds with antes, and you're supposed to go all in instead of raise. Which of these hands do you go all in with? It's roughly the same range. So yeah, I think as a decent rule of thumb, if you just go all in with the same range, you're not going to be doing badly. But when the effective stack size is much smaller, like let's say you only have 3 big blinds, then you can drastically increase this range. Okay, so when your effective stack size is actually, say, 10, or let's say your effective stack size is 5 big blinds, intuitively you might think, I can wager a lot wider a range of hands. So here's the argument. The argument is, I'm only risking 5 big blinds. In the other case, I was risking 12 big blinds. Why should I should be way more aggressive with 5 big blinds than 12 big blinds, right? So that's the argument, but the reason why that argument is wrong is because with 5 big blinds, you're going to get called every time. With 5 big blinds, you can't just go all in with 7-2 offsuit because your opponent has such good odds to call, they're going to call you. Whereas with 12 big blinds, even though you're risking more, you also have more chances of getting everyone to fold. So even though it seems like you're risking way more, in some sense you're not. Because the more chips you're risking, the more likely it is that everyone else folds. Does that argument make sense to everyone? So make sure you don't get tricked by that, because it is easy to get tricked. But the fact that when you're risking more, you're getting people to fold more, means you're actually not risking as much as you think you are, and that's like a common fallacy. Okay, cool. So, so we're near the last part of the class. So, are there any other questions? So I know some of you probably want to start playing tonight, and I definitely did not address everything you need, but. Are there any other questions, roughly in terms of opening and going all in, that you might want to know before, like playing tonight? Because I do think we have maybe 5 extra minutes, so I can answer some questions. Does anyone not know what the term like bluff means? I said bluff a bunch of times, but I realized I never explained. So bluffing essentially means you have a bad hand, and because you have such a bad hand, you know the only way of winning that hand is to get your opponent to fold. So basically, you bet big to hope that your opponent folds. If you have a better hand, like an average hand, often you actually don't want to be betting because there's no point. Because when you bet, you're essentially just getting adversely selected where your opponent calls you when their hand is better and you lose more money to a better hand, and your opponent folds when their hand is worse, so you're not making any money from a worse hand. And then with your best hands, you want to bet to try to get your opponent to call and increase the amount that you win, and we call this value betting. So I'm going to get more into this in future lectures, but essentially in poker, the paradigm you want to play is you want to value bet your very best hands, and then you want to basically check and try to get to showdown, like try to show your hand on the river with your medium hands, and then also bet with your bad hands to try to get your opponent to fold better hands. Okay, I'm going to get to the last part now. Okay, so quick tests. Okay, so here, what would you do? It's folded to you, you're in the hijack, you have ace-5 of clubs. So someone want to suggest what would you do? What would your play be?
Every $5.
Call.
Raise. Okay, good. Raise. So not call. That was mistake number 1 to not do. You always want to raise the blinds. But it's fine. It's fine. That's fine. We're all here to learn about these hands. Okay. Now, should I go all in or should I just raise to 450, which is 2.25? I should go all in. So, okay, I think it's not terrible to just raise to 450, but I said if it's 10 big blinds, there's no antes, right? So you need 10 or less, and you have 10, so going all in I think is fine. Okay, so we decide to go all in. And yeah, so roughly this is what, so there are Nash calculators. They're complicated, but if you run this through a Nash equilibrium calculator, this is roughly what you should be going all in with. Okay, so we go all in. So this range is a bit different than what I showed you before, because this is an actual Nash calculation, not just my recommendation. It's going to be wider than what you saw before, but that's fine. Okay, so now you're this guy, you're seat 9. Okay, so I'm going to show you how to do a quick calculation of what equity you need to call here. And I'm going to, so what equity you need to call here. So a straight up pot odds calculation says you're getting 23 to 20 or 1.15 to 1. So you roughly need 46.5% equity to call as this player. But there's 2 players behind. There's a graphics glitch. Seat 1 has not folded. Seat 1 and Seat 2 both has cards. So you actually need more than 46.5% equity, because the calculation of 46.5% assumes Seat 1 and Seat 2 can't wake up with pocket aces. So, so PokerStove is very good for this, and you can do this right now. I've taught you everything you need to do these calculations. And PokerStove is also easy to figure out how to use. You can essentially just plug in, you look at pocket 5s, it has 48%, you need 46.5%, And I said you need a bit more than 46.5 due to the fact that there's 2 players behind. So pocket fives, you know, it's good enough. Okay, well, I'll call. Ace-9 suited, I'll call. So I'm just showing you some calculations on PokerStove. It really is a really good tool. So you can do some calculations, and you... Okay, so basically, okay, they call. And the hands I showed you here is actually sort of the worst hands that it's plus EV to call with. Pocket fives, ace-9 suited, plus. So ace-9 suited plus means ace-9 suited, ace-10 suited, ace-jack suited. All the hands that are strictly better than ace-9 suited. Ace-10 offsuit, king-queen suited. Okay, so now, as the last player here, do you call with king-queen suited? Just rough guess. How many of you intuitively would call with king-queen suited? So 2 players have already gone all in. So most people would fold. Oh, you guys are calling. Okay, so it turns out, at least according to the Nash calculator, which is not... So here you calculate the pot odds, and this is an exact calculation because there's no more players behind. So you just calculate, do I have 29.5% equity? And basically, if I assume that player 1 and player 2 are playing according to Nash equilibrium or optimal ranges, you actually have way more than enough. You actually have 34%, where you only needed 25%. So this was sort of a trick question I set up. The trick was, king-queen suited doesn't seem like a good hand, but against 2 other hands, it's actually relatively a very good hand. You know, against one other hand, they could just have a pair and you're behind. They could have an ace most of the time and you're behind. But against 2 other hands, you actually have really good equity. Because when you hit a king or a queen, you have a big pair. You can also hit straights and flushes with king-queen suited. And your equity against 2 other hands is very good. Okay, so you have way more than enough, so they call. Okay, so we're going to get in this all in pre-flop. Okay, so who are the people I gave these cards to? You guys can come up to the front, and I'm going to hand you your cards. The people who I gave these gift certificates to, who I said.
Yeah.
Yeah, stay up here, stay up here. Okay, so what I want you guys to do is, okay, so these are the hands people went all in with. Okay, so who was the first person to answer? Okay, so you get to pick. Which hand do you want?
Yeah. I'll go with Jack.
Okay, so Colin. Colin is going to take Jack. Okay, sorry, what's your name?
Kevin.
Kevin, which hand do you want? So he took Jack. Which of these remaining? You were second, right? Yeah, you were. Okay. Okay, which hand do you want?
I want king queen.
Okay, so he's going to take king queen suited, so you're going to take ace 5 of clubs. Okay, so this is sort of mean, but I want to show you guys, this is how poker works. When you've already won, you've won $20. So you guys are going to put your money in, and whoever wins this hand is going to get all 60. Because the poker, the winner takes all. Okay, so this, we're going to go forward. Predetermined. Okay, so this is the pre-flop equities. So it is predetermined. Okay, so it looks like you guys did very well. You guys picked correctly. You got to pick first. You picked the best hand with equity of 34.73. You got 33.95. You're only a bit behind with 31.1. All right. Okay, so the flop is 6, 7, 8. So let's look at the probabilities now. Jacks is still ahead. Ace 5 has picked up a lot of outs. King Queen of diamonds is not looking too good, but they did pick up 1 diamond. Okay. Darn. Turn is the 9 of hearts. So I'm sorry. Wait, you guys King Queens? I'm sorry. So you're out of the running. And then
He needs a 10.
okay. Do people want to cheer? Is there any card you're hoping for? What are you hoping for?
Yeah.
10 or a heart.
Oh.
Okay, so you want to be screaming, okay, I'm going to press it on the count of 3.
Okay.
You want to be screaming 10 or higher. And you want to be screaming, not anything else. The 10 of spades. Okay, so I guess you get all 3 of this. But there's going to be more of these gift cards during class. So participate in class. You're going to get gift certificates courtesy of the Cuban Cabbage. All right, thank you guys.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, guys, I'm gonna get started. If you haven't done attendance yet, you can do it at the break or afterwards. Anything will work. Okay, so just a few quick announcements. So homework 1 is posted and due Friday. I had it up on here. Are there any questions about homework 1 or anything about the procedure? So Lee Marie is going to have office hours shortly after class, 4:30 to 5:30 in E51 145. So if you have any questions, you can ask her as well, or you can ask me now if you think they're applicable to the general class. Okay, cool. So I'm going to proceed then. So I hope, so most of you I think have started playing in the online tournaments. I hope you guys, if you haven't, I hope you plan on starting soon. I hope they've been fun so far. Okay, so today I'm going to focus more specifically on poker itself. I know last class I talked about a lot of general concepts on decision making and how to think about, exploiting your opponent versus playing in a Nash equilibrium way. Today I'm going to focus mostly on poker and try to give a lot of hand examples. And I'm going to introduce post-flop play, which I didn't really talk about last time. So basically what happens after you see the flop. Okay, so I'm going to just start with an example hand. So we get ace-queen offsuit in hijack -1. So I think I called it low jack in an earlier slide in last class, but basically it's 4 away from the button. So it's how many people, the thing that matters is how many people behind have cards and could be left to act. So we raise a bit bigger than 2.25 big blinds, but I'm not going to nitpick that for now. So we're a bit deeper stacked, so we want to build a bigger pot because we think we have an advantage, I guess. Okay, so it's folded to both blinds and both blinds call. Okay. So the flop comes 9-8 deuce. So we sort of missed the flop, and the small blind checks and the big blind checks. Okay, so what happened is clear so far. Okay, so now we have a decision here essentially. So first I want to talk about checking to the pre-flop aggressor. So this is sort of a conventional way to play. So they both checked. So we were the pre-flop aggressor. So in this case, I mean by pre-flop aggressor, the person who put in the last raise pre-flop. And the reason why this is significant is because in some sense, we have a stronger range of hands than they do. Because we could potentially have pocket aces, which is the best hand. And it's going to be a good hand on pretty much any flop. Whereas it's much harder, it's much more unlikely for them to have pocket aces. Because if they had pocket aces, it would be a good play and a tempting play to re-raise pre-flop. So basically, they're sort of just recognizing the fact that, on average, we're going to have a better hand than them. So they're going to check to us and let us bet. Because in general, on average, they would prefer if the pot was smaller, and we would prefer if the pot was bigger, because our range is better. So, so they both check to us, and so like let's say they had a pretty good hand. Like let's say small blind had 10-9 suited or something, which is the top pair, so the highest pair on this board. That's a pretty good hand, but that's still a hand that loses to pocket aces, and there's still the risk if he bets out with 10-9, we could just raise, and then he has to be worried, do we have pocket aces? There's basically always going to be this worry of pocket aces and pocket kings and just big pairs that he has to worry about that we have to worry about less. Occasionally someone there probably should slow play pocket aces pre-flop and just call, but most of the time it'll be a better idea for them to re-raise to get more money in pre-flop. So that's why they both check to us. So now we have the opportunity to bet or to check back. So let me first talk about how big to bet if we decide to bet. So here we bet 200 into 375, which is about half the pot. And so between betting big and betting small, it's sort of the same principles I talked about last class between raising big and raising small pre-flop. So the advantage of betting small, so the disadvantage of betting small is that you give your opponent better odds to call. So like let's say they have, I don't know, like Jack 10 here, a hand that's losing to you, they have a better odds to call and a cheaper price to call to see another card to try to beat. But on the other hand, our hand isn't amazing. Our hand isn't good here, essentially. We've missed the flop. We haven't paired our hand. And if we get raised, we're probably going to have to fold. And the more we bet, the more we lose when we get raised. So it's the same sweet spot principles. If you bet too small, you get called too often by worse hands that can just have good odds to call. And if you bet too big, you're just losing a lot when you get raised. So a good rule of thumb is to bet half the pot on the flop, and then like a slightly bigger percentage on the turn, like 60%, and then an even bigger percentage on the river, like 70% or something. Something like that is about reasonable. You could bet up to like 100% of pot on the river. So I'd say just somewhere between 50 to 100% of pot is a good amount to bet, and the fraction should increase as you get closer to the river. So this might seem slightly contradictory, because what I said last class was last class I said you don't want to give your opponent great odds. But in some sense, if we get to the river, right, all the cards have come out. There's no more unknown cards. So either they have the better hand or we have the better hand. But there's going to be no uncertainty in what cards could still come. So in some sense, you might think it's more intuitive to bet smaller on the turn and river and bigger on the flop. Because on the flop, they have more chances to outdraw us. Whereas on the turn and river, they have fewer. Let me just find all right, now I don't know we stand there. Okay, so this might seem contradictory, right? So I'm saying that bigger on the river, but on the river, they actually have, in some sense, it's more determined whether their hand is good or not. So why is this? Why do we want to bet bigger on the turn than the flop, whereas on the flop, any hand sort of has closer to 50% equity, because anything can still happen with two cards to come. So the main reason is because when you bet the flop, they're not just deciding to call your flop bet for the equity there. They also potentially have to call a turn bet and a river bet. And essentially, this factor, the fact that you can threaten to bet again on the turn and bet again on the river, and they have to call all these bets, is a bigger factor than the fact that there's slightly better odds to call on the flop. Okay, so another important thing to say is when I said bet between 50 to 100% of the pot, I mean, I think it's very important to bet at least some fractions of the pot, especially when they're checking to. Because in some sense, betting small is strictly worse than checking. Like, in this case, you bet 50, which I guess isn't nothing, but imagine you bet $1 here. The issue with this is the rules of betting say, right, if anyone bets any positive amount, then the guys who checked now have a chance to check raise. So if you're betting small, which is almost the same as checking, all you're doing is giving your opponent a free option. You're allowing them the opportunity to say, okay, I could have just, like, if you check, you see the turn, and the turn comes. But by betting, now they have the opportunity, a second chance to bet. Yeah.
How does this change if you have, like the nuts? Should you bet? Like, you want calls at that point, right?
Right, exactly, yeah. So I'm going to get to that, yeah. So if you have a good hand, yeah, you'll bet too because you want calls. Right now I'm just talking about a general strategy to play with your entire range of hands. And in general, I guess that's how I'm trying to encourage people to think about poker in this class. Like, instead of thinking about what cards do I have and what cards do my opponent have, I try to talk in terms of what is the probability distribution over my opponent's hands and what's the probability distribution over my hands and his hands, essentially. So I'm just talking about a general scenario, yeah. Okay, cool. So you never want to bet too small, basically. It's better to just not bet. There's no point to bet really small because you're giving away a free option. Okay, so this is what I just said, essentially. Because remember, just because they checked doesn't mean they have bad hands. They're often checking regardless for the reasons I described earlier. Okay, so in this situation, with ace-queen offsuit, I think both betting 200 and checking are reasonable plays. And let's analyze the advantages and disadvantages of both. So the advantage of betting 200 is that you don't give some garbage hand like king-jack a chance to outdraw you. So in this situation, if we bet 200, probably if someone had king-jack, they'll probably just fold because it's almost one of the worst hands on this board. And if we bet 200, then they're going to fold, and then we could just win the pot right there. If we don't bet, maybe the turn will come a king or a jack, and they could beat us. So what's the advantage of checking? The advantage of checking is we get to see the turn card for sure. We can't get check raised. Like right now, if we bet and we get check raised, we probably have to fold with no pair. But if we check, we might see a queen or an ace on the turn, which would be great. And another advantage of checking is, in some sense, when you bet in this spot, you're only called by hands that beat you. You know, you're going to get king jack to fold, which is still fine because they have 6 outs, but you are ahead of them. So it's not the end of the world to just check. And you know, if the turn comes like a deuce, you're still ahead. And if it checks all the way to showdown, like all the way to the point where you have to flip over your cards, you're still going to beat king jack. Whereas when you bet, you're essentially getting all the hands you're ahead of to fold. Like if they have ace 7, which you're also ahead of, they're probably going to fold. And pretty much all the hands that beat you probably aren't going to fold. Like maybe someone will fold pocket 3s or something, but for the most part, you're going to get called by a 9, you're going to get called by an 8. So it's this idea of like sort of adverse selection. You're getting called only by hands that beat you, and you're just folding out everything else. So overall, I'd say these about balance out, and you can, I think betting or checking are both fine. Okay, so now let's suppose it's the same spot and we had king-queen. We had king-queen instead of ace-queen. So pretend all the action was the same. All the pre-flop action, the flop action, everything was the same, except just our cards changed. So in this case, if we do the same comparison again, we'll see that betting has a bigger advantage now, because we can get hands like ace-jack and ace-7 to fold. Those hands previously we were beating with ace-queen, but now we don't want to risk getting a situation where it's checked to showdown and everyone flips over their cards and we lose to ace-jack or ace-7. So I'd say in this case, now with king-queen instead of ace-queen, betting has a lot more advantage because we're getting better hands to fold. Okay, and this is what you're talking about. Yeah, what if you have the nuts? So in this case, so suppose now we change our king to a queen, so we actually have a really good hand. We have pocket queens, which is an overpair, a pair above any card on the flop. So now let's look at the advantages of betting versus checking. So now the one advantage of betting that we never had before, because we always had bad hands, is now we can get worse hands to call us. If they have 10-9 or ace-8 or pocket 5s, they're probably going to call, and we're beating them, so we're just going to win more money. And the advantage of checking is essentially none. So the correct play, I think, is clearly to bet in this situation. So essentially what I'm trying to get at is, so I call this the fundamental theorem of poker. It's sort of a made-up term. But essentially, so one of the main things you should realize when you're betting post-flop is a bet basically accomplishes one of two things. So with your good hands, you want to bet because you can get them to call with worse but still good hands. And we call this value betting. So with the pocket queens, this is what you're doing is value betting when you bet. And then with the bottom hands in your range, you should bet to get them to fold better, but still pretty weak hands. So in this case, when we had king-queen, we would be betting to get them to fold ace-jack. So this is called bluffing. So essentially the point of a bet should either be a value bet because you have a really good hand, or a bluff because you have a really bad hand. And you want to sort of think in terms of that way. And you know, if you ever find yourself making a bet and you're not sure whether it's a value bet or a bluff, then chances are you maybe shouldn't be betting. So with the middle hands in your range, you should check, because if you bet, you fold out all the weaker hands and you keep in all the stronger hands. Okay, does that make sense? So this is like the fundamental concept in poker, essentially, that we should try to realize. Okay, so I sort of made this diagram. So the best hands are at the top of the rectangle, the worst hands are at the bottom. So once again, we're thinking in terms of our entire range of possibilities. So post-flop, we want to so that's on the left. Post-flop, we want to bet the best hands, bluff the worst hands, and then check things in the middle. And then pre-flop, basically we fold all the bad hands, and then we raise, or if someone's already raised, we re-raise the best hands, and we just raise the pretty good hands. I'll talk more about pre-flop in a future lecture. But I just wanted to contrast this because I don't want someone to think, you know, if I have 7-2 offsuit pre-flop, I should be bluffing. Because it's a different scenario, because pre-flop you're choosing what percentage of hands you play, and it's strictly better to just choose the best 30% or the best 40% instead of choosing the best 10% and the worst 10%. Okay, so going back to this principle, with 7-7, so it's still the same situation. So I'm analyzing the same situation many, many times with different cards. With 7-7, the right play is definitely to check. Because, so with ace-queen, it's in a similar spot to ace-queen in that it's also, you get called only by better hands and you mostly only fold out worse hands. But with ace-queen, at least there was the advantage that if they called with like an 8 or a 9, we could turn, we have more chances to beat them. We could turn an ace or a queen and win more money, or alternatively, we could like turn a jack, which gives us a straight draw, and try to bluff them off of their 8 or something. Whereas with pocket 7s, there's less room to play. So I think with pocket 7s, you should definitely check out this flop. So some other stuff about continuation betting on flops. I wouldn't bluff super scary flops. By super scary, I essentially, mathematically, it just means there's a lot of uncertainty because so many things are possible. And basically this happens when there's 3 cards of the same suit and they're all connected. So whenever the board is like this, it looks scary, it looks very coordinated, but mathematically speaking, it's essentially saying anything can happen and no one should fold if you have anything at all. Because, if you have any 10, you have a chance of making it straight. If you have a reasonable heart, you have a chance of making a flush. Just any hand is going to have a reasonable chance. Same as, even if you have like an ace, like I guess as we do, you have a chance of turning a higher pair. So I would just check and basically give up on this flop, or check and hope you hit an ace or a queen, I guess. And another thing is continuation betting into too many people if you have nothing. It can be an advanced play in certain situations if everyone else also recognizes that, if you're continuation betting into 5 people, you must have such a good hand that they're going to fold a hand as good as, say, like pocket 8s here. But for the most part, in practice, I would say if the pot has like 6 or 7 people, I wouldn't try to bet on the flop with overcards to try to get everyone to fold, because someone's going to have 2 hearts, or someone's going to have a 7, someone's going to have a pair. Okay, so I talked about sort of when you want to bet post-flop. So now I'll talk a bit more about when you want to call bets post-flop. And I'm going to try to give a lot of different situations. So now let's look at calling bets. And I think newer players especially tend to call with hands weaker than you need to. So the general rule of thumb is unless your opponent bets extremely small, which they should not do by what I explained, you should fold most of your hands to a half-pot bet. So in some sense, most hands miss most flops, and when you miss, there's really not a reason to do anything other than to fold. There's a lot of tournaments, you can always play the next tournament and get dealt a new hand and try to have a good hand. So, so now I'm going to change the situation up a bit, but once again, I'm going to analyze the same betting situation over different hands. So now everyone folds to the button. We're still 40 bets deep because the blinds are 25-50 and we have 2,000. And so the button makes it 125 and we decide to call with our hand. Okay, so let's say we have queen 9 suited in this case. And okay, let's say the flop is 10-7-2. So we check. We check as a form of respect to the pre-flop raiser, and then they bet half pot. So here, this is a situation where we've got no pair, no draw. I guess we have an overcard. We have an overcard in the queen, and we can turn a pair of queens to beat his pair of 10s. But that's only 3 cards that help us. Basically, the correct play is just to fold. You essentially have nothing here. You have some speculative straight draws where if you hit a jack and then an 8, like if you have 2 cards that come for you, then you can do a straight. But for the most part, we've got nothing. We just fold. Here are some other situations where you should just fold. So here we have ace high, but the board has 3 pretty big cards, and there's a decent chance he's going to have one of them. And if he doesn't, he's going to have like queen 10 or 10-9 or something with straight, or some kind of straight draw with a lot of outs. So there's just no reason to play hands like these. So it's totally fine if you lose a lot of hands, as long as you win more chips on the hands that you do win. So just fold this, not much reason to play. Here you have, this board is a bit better for you. You have ace 9 high on a 6 high board, but there's a lot of straight draws and there is a flush draw, a spade flush draw on this board, so I would still fold. Here we even have a pair, but this is an example where I think I'd fold even though you have a pair. So we have a pair of nines here, which is decent, but once again, there's 3 hearts, and it's easy for him to make a flush or make a straight. And even if he doesn't, we're gonna have to check to him on the turn, check to him on the river, and then they can bet, and then we have to decide whether to call or not. So just overall, it's gonna be tough to play. And this is what I'm talking about being out of position. So we have to act first on every street. So it's going to be tougher to make good decisions. Okay, so now we're getting into some better hands, but I think I would advocate still folding these. So here our hand it's not bad. We basically got a 4-out straight draw, which is usually called a gut shot. You need to hit an 8 to turn a straight. And also we've got diamonds. If we hit 2 diamonds in a row, we can make a flush. But overall on this spot, I would still fold just because even though we've got 4 outs to our gut shot, we've got no combinations. We've got no other combinations to help us. Like a 9 is essentially useless when there's 3 higher cards on the board. Turning a 9 doesn't help us at all. Turning a 7 doesn't help us at all. And furthermore, even if we turn an 8, it's possible. So if we turn an 8, then Queen 9 makes a better straight than us, and also King Queen, which already has a straight, is a better straight than us. So even when we hit an 8, we're not even 100% sure we're going to win the hand, and we could just put our chips in after hitting an 8 and lose all our chips. So I would fold this as well. 4-out gut shot is pretty bad unless you have other stuff to go with it. Okay, so in this case, we have a better straight draw. So in this case, we have an 8-out straight draw. Because an 8 gives us a straight, 8 through Queen, but a King also gives us a straight. We have 9 through King. But in this case, I would still recommend folding just because if a King comes, then we do have a straight, but we lose to an ace. So 10, Jack, Queen, King, Ace is going to just be a higher straight than our 9 through King straight. So even though we have a lot of outs, the outs aren't that good, and it's possible once again, we make a second best hand, which is the worst possible situation in poker because you're going to put a lot of money in and you're going to lose. Okay, so this is another example I would fold. Pocket 5s on Queen, Jack, 10. You have a small pair. You started with a small pair, but you didn't improve at all. The flop did not help your hand at all, and it most likely helped your opponent's hand. Okay, so here's a question you can ask. So in all these spots I say fold, but what if I think bluff raising will work? What if I think I can get him to fold if I raise? So what I want to say is when you're bluffing on the flop, it's usually because you have some kind of draw or some kind of nice speculative hand that has a chance of turning into a good hand. And all the examples I showed, not only are our hands bad, there's not that many good cards for us, with the exception of maybe the 7-9 hand, where if you turn an 8, it's pretty good. But yeah, even this hand, if you turn an 8, it's not that good because the board is then going to be 8, 10, Jack, Queen. So we're only playing with a 1-card streak, which is still fairly easy to put aside. Okay, so before I get to spots where maybe we want to raise, potentially bluff raise, let me just go through some spots where I think calling is a pretty good play. So here, I think calling with ace-9 high on this board is reasonable. In the example where I said you should fold, the flop was 6-5-4, and there was a flush draw. So there were straight draws and flush draws. In this case, the board is paired, which really helps us because there's just fewer combinations of pairs that he can make. And a 3 is a pretty small card, so it's pretty unlikely they have a 3. So ace-9 high is pretty good here. You have 2 overcards. You even have a diamond backdoor flush draw. So I would call here. Okay, so so getting better here. This hand is even better. We have ace-3. We have bottom pair on this pretty safe flop. It is 3 different cards, and they could have a jack or a 5, but just overall against their range, we have tremendous equity here. So I would call. So note when I say call, not raise. I'll give you examples of how good, roughly speaking, our hand has to be to raise. Alright, so here I would call. The board is very scary, but we have second pair, and I think second pair is just second pair with the best kicker, the ace. So that's definitely good enough to call. With ace-9, I think this would be borderline whether you call. I think calling is okay, but not mandatory. Okay, here's another example. Second pair on a safer board. This is a pretty good hand. I mean, if they've got an ace, we're not drawing to that many outs, but if they don't have an ace, they're not drawing to that many outs. So it's because whenever big cards come on the flop, like an ace and a king, in some sense, even if there's flush and straight draws, more of who's going to win has been decided. Because if you've got a big pair, like if you've got an ace or a king, then there's not like an even bigger card that can come on the turn to beat you. And if you don't have it, then you know, like if you have 10-9, even if you turn it 10, you're not going to outdraw ace 7. So here I would just call. Here you have a pretty good pair, pocket eights on 9-3-3. Obviously you have a very good hand here, but I just think in this case where there's no flush draws, no straight draws, there's not really that much reason to raise, because it's not like you're going to get called by worse hands that often, that I would still only call, even though in some sense your hand is very, very strong here. Like I would expect you to have the better hand more than 80% of the time, but the problem is when you raise, they're only playing the 20% that beats you, which is hands with 9s, hands with 3s, and like pocket 10s plus. So here I would also recommend calling, even though we have top pair. So top pair, the highest pair on the board. It's a pair of aces, which seems, it seems like we have a good hand, we should raise. But once again, our other card, which is very relevant, is very small in this case. So we're going to lose to ace queen, any kind of big ace. And furthermore, there's not that much reason to raise, because we're not that scared of letting him see a turn card with, say, 10-9. Because even if he turns a 10 or a 9, he's not going to beat us. So the reason to raise is essentially do not let your opponent see more cards and give them outs, but they don't have that many outs if we're ahead of them. So this is, you can say this is like a way ahead, way behind situation. That's some terminology that you might hear, which basically means you're either way ahead because they don't have an ace, or you're way behind because they've got ace queen. And when you're way ahead or way behind, you don't really want to be raising, because he's just going to call you when you're way behind, and he's just going to fold when you're way ahead. Okay, so here we're getting into some pretty good hands. Ace jack on jack 10-9 with a flush draw. I think if you raise, it wouldn't be the end of the world. The issue is I think 2,000 chips when the blinds are only 25-50 is still a bit much to put in your entire stack on this flop. And just because even though you have top pair with the best kicker, there's a lot of straights, and even if let's say they have like queen 9 of hearts, a hand that's behind of you currently because they only have a pair of 9s, there's just going to be so many straight and flush outs they're going to have that you're never really getting it in ahead of equity by that much. So I would just call and see what the turn is. But that's maybe the best, one of the examples of the strongest hands you can have where I would still recommend calling. In this case, we've got a small overpair, but I would still call, even though once again we have the best hand probably 80% plus of the time. But once again, when you raise, you're only getting played back at by the 20% that beats you. So, okay, yeah, and notice there, when I went through these examples, the stack size was very important, right? So from the first class, the important things are position, stack size, and cards. In this case, the position was the button, the cards, I've showed you what the cards are. But the stack size, the fact that you're playing for potentially 2,000 chips is very important. And if you're playing for fewer chips, then you can risk gambling a lot more, as I'll show you later. Okay, so another note is you could argue for check raising in some of these call situations, especially the ones where your hand was more vulnerable to overcards. So let me just quickly run through them again. So I'll describe what they are. So this is one of them. Because here you could argue, okay, I want to raise because if I call, what if he has jack 10? Then he has 6 outs, right? Here, this is another example. What if they have 10-9? They can turn a 10 or a 9 and beat us. Here, this is not an example. Here, I think calling is clearly correct because the only bad cards are like a queen because an ace gives you 2 pairs. So there's just very few scary. The board is already scary and there's not that many overcards that could come. This is another example because in this case there's actually no scary cards in some sense. There's no card that you're afraid of giving him. this is an example where you could argue for raising. You know, you don't want Jack 10 to see another card. That's reasonable. Yeah. Here, there's no risk. It's completely safe, so I would never raise. Here, I guess there are some bad cards, but it's if you raise, they can just call with their draws anyway to try to hit. So here, this is an example where you could argue for raising to not let them see a turn card. Okay, so yeah, these are reasonable arguments, and I think raising some of these call hands would not be a terrible play. But I think for most of these, the advantages of calling still outweigh the advantages of raising, especially if your opponent is also capable of bluffing. Because, like, let's say you check raise. So let's say they make it 150, you make it 400, and then let's say they go all in. But they're going to go all in not only with hands that beat you, like pocket sevens plus. They'll also occasionally do this with hands like ace 3 or ace 4, hands that have an overcard in the ace, but also have a gut shot straight draw, like ace 3 or ace 4 can make it straight. Then you're just in a very tough spot. Basically, if you call, you're not in a good situation because you're often behind. But if you fold, then you're also folding to a lot of weaker hands. So there's just a lot of ways for the hand to go badly if you raise, because your hand sort of, it's not good enough to raise and call if they re-raise, yet it's too good to sort of waste as a check raise bluff and just like fold if they re-raise, right? Like let's say my plan here with pocket sixes is to check raise and fold if they do anything else. But then, like, you could argue, why am I doing this with a hand as good as pocket sixes? Why don't I do this with 10-9? Because it's going to be a similar result most of the time. They're going to either fold, and I'm going to win the pot with 10-9, or they're going to raise, and I'm going to have to fold with 10-9. Occasionally, they'll call, but you could argue in that case, I would almost rather have 10-9 than pocket sixes, because pocket sixes, I'm just going to always lose, and 10-9, who knows, I can turn a 10. So, anyway, so the long story short is I would just recommend just calling with most of those hands, although there's definitely lots of arguments you can make for raising. Yeah.
I didn't get why wouldn't you want to be raised if you have the top pair and top king? Because if you give them the draws, at least you want to make the pot bigger than it is right now, right?
You're talking about this situation?
Yeah.
Okay, yeah, that's a good point. Yeah, I think that the main reason is just your overall equity against their range is pretty low on this board compared to an average situation if you have top pair, top kicker. Like if the board is Jack 7-2, your equity against their range is probably something like 85%. Whereas on this board, your equity is just overall a lot less. There's a lot more hands that beat you, so there's a lot higher probability that if you raise and call and put all your money in, that you're behind, basically. So there's just a huge risk of that. So, but yeah, I do agree. It does feel very unsatisfying to only call and let them see those cards, but I think it's sort of the lesser of two evils in this situation between putting all your money in with this hand versus letting them see some cards. Yeah. All right, cool. Okay, so just how good does my hand have to be to raise? And the question depends on the effective stack size. But when the effective stack size is fairly deep, so let's say 40 big blinds, I think, is about 40 big blinds or deeper. So, you have a lot of chips, you're playing for a lot of chips relative to the blinds. You need a pretty good hand to want to put all your money in. So a general rule of thumb is 2 pair or bigger. And yeah, once again, this is only applicable when the effective stack size is large. And a lot of the online tournaments, especially the ones where the blinds go up quickly, the effective stack size can be around 10 or even lower pretty quickly. Yeah.
How much do all these decisions depend on their position for your position?
Okay, that's a very good question, actually. Right. So in this situation, so the answer is essentially, yeah, it depends a lot. And the examples I gave are specifically for the button. Yeah. So I would say if they were under the gun instead of the button, you need to play somewhat differently because they're going to have, because on the button, they're going to have 55% of hands. And let's say here, like 10-9 is a possibility. But actually, maybe a better example is, I think this is a board where it's really different because against if they raise from the button, you know they could have 55% of hands, and ace 3 is a pretty good hand here. But if they raise from under the gun and they're pretty tight and their ranges, pocket 8s are better, and ace queen, ace jack, ace king, then you're doing a lot worse. Yeah, so it definitely matters a lot, and yeah, I mean, so I guess I can't go through every single possibility, right? Like this position, this stack size with this, so you do have to do a bit of extrapolation. Like if they're right now in these examples, they're the button. If they're the cutoff, their range is going to be a bit stronger. If they're the hijack, their range will be a bit stronger. Yeah, that's a very good question. Yeah, very, very good point. Yeah, because in all the analysis I just did, I'm assuming their range includes hands as bad as like 8-7 suited and stuff, which isn't going to be the case if they were earlier positioned. Okay, so, all right, so how good does my hand have to be to raise? So 2 pair or better, but by 2 pair or better, I mean 2 pair where both of your cards make a pair. Here, where 1 pair is on the flop, I wouldn't count this as 2 pair. And this 2 pair is complete trash because any card beats you, so I wouldn't go on here. This one's also pretty bad. So okay, so now when would we raise? Okay, so I think this is basically the best thing that can happen to you in poker, pretty much. Almost this exact situation. So here we got we got 3 of a kind, and there's also a lot of draws, so we're going to get played back at a decent amount because he could have hearts, he could have like queen jack. There's just so much stuff that isn't going to fold, and we're always going to be way ahead, pretty much always going to be way ahead. So yeah, I actually think this is very close to the dream situation. Does anyone have an idea why this situation is almost in some sense even better than, say, we had pocket 10s? Yeah.
If you have pocket 10s, that's like 8 out of 10.
Exactly. Okay. All right, I'm gonna give you a $20. No more playoffs today, so you can see. Okay. Right. So it's almost even better in some sense. You have pocket 5s because, as Ben said, if you have pocket 5s, he can have a 10 and put in a lot of money. If you have pocket 10s, even though you're crushing even harder, it's almost like you've taken all the good cards away, and he's just always going to fold. So, okay. Here's another situation where your hand's very good, although I think you can make a case for just calling here. Yeah, I don't want to say you have to raise because your hand is just so invulnerable, and even though the chances that he has the remaining ace and a better card to go with it is pretty small, there is still a lot of, I guess, like adverse selection in this case where, because there's no draws, when you raise, he will fold a lot of stuff. And the stuff that he does play, it's not going to only include the remaining ace. Like he will call with pocket 7s almost certainly, but it does include it does significantly make his range more likely to be the ace that beats you. So I think just calling is okay. Here, obviously, you have the best possible hand. Although once again, I think just calling as a sort of a trap is reasonable. Although I would advocate just raising. I think it's the simpler play. Calling, I think you'll see a lot of high stakes players do as a trap, but it's a very, very tricky play. I think raising definitely has lots of merits because, like, if they've got king, like even ace king, they're not going to fold. They just want to get all the money in because they're probably going to think you're more likely to have a single heart than 2 hearts. So if they have ace king, especially when it's only 40 big blinds, they're probably just going to be happy putting all the money in, and before you can see a 4th heart. So, like in this case, even though you don't need a 4th heart to make a flush, a 4th card is a really bad card for you because that sort of kills all the action you're getting from a king, from a pair of kings or something. Yeah. Okay, so this is a similar situation, although in this case I would say a raise is mandatory. In the previous case, I think it's not mandatory because your hand is so safe. If you decide to try to trap your opponent, you'll never end up trapping yourself. Whereas here, if they just have any heart higher than a 6, if a 4th card comes, they're beating you now. And worst of all is, let's say they have 10 of hearts, 9 of diamonds. If you raise, you could have easily gotten them to fold that 10 of hearts, probably. Although the 10 of hearts, 9 of diamonds is a bit good. Let's say like 9 of hearts, 8 of diamonds. They almost certainly would have folded their higher heart, and now you just lost an entire pot because you didn't raise. So here I would raise. you have a straight, you are drawing dead if they have a flush, but with only 40 big blinds, I think the chances of a flush is unlikely enough. Getting it in is okay. With 100 big blinds, you could still raise, but probably not go all in. 2 pair, the board is sort of scary, but 2 pair is definitely good enough here. So, all right, so these are examples where you had really good hands, and I said you should just raise and get the money in and be happy about it. So do I need such a good hand? There's some other situations where a 1-pair hand is sort of good enough. And so coming back to the ace-jack example you asked, so we'll see some of that. Okay, so in this case, I think if you have pocket aces, that's definitely good enough to get it in, although you shouldn't have pocket aces that often here because most of the time you should be re-raising pre-flop. But you know, if you decide not to raise pocket aces pre-flop and you end up with it here, then I guess raising is good. You're going to be having the better hand. Although, you know, if you were trapping them pre-flop, maybe you just want to trap them again and call again, since there's not that many scary cards. So here's an example of an ace-jack situation where I think getting in is fine, just because there's still draws and there's still lots of worse hands that will give you action, but overall your equity against their range is much, much higher on Jack-7 deuce than Jack-10-9. So I would just raise and be happy getting in 40 big blinds here. Here's a similar example, King-Jack, but we've also got the second best flush draw, so it's just very hard to get it in bad. Okay, so we'll see some examples where we have fewer chips. So in the last case, all the hands, we essentially had 40 big blinds, essentially had a lot of chips. So now let's look at a situation where all the players, so we only have 12.
Hey, what's up? Come with me skiing on a day in a complete boondoggle. I was actually there for a Cloudflare event. They have a relationship with the U.S. ski team. You can see some of them right there. And they provide technology to them and work with them as far as helping protect them. Okay, so we're good to go. I did not indulge. Remember, I'm on the clock here, so really the whole world in front. But yeah, here's another video from when I got to actually hit the slope. So this is the gondola you take from. We're kind of few and far between me trying to pretend that I'm a ski bro now. Okay, thanks, bye.
But when I'm only 25,
what's up? Come with me skiing on a day in Davos. So my name is Danny Francesco. I write Business Insider's daily newsletter, and yeah, I'm in Davos, and I got to actually hit the slope. So this is the gondola you take from Davos up to where you can ski. It had actually been, now that's me on the lift, it's actually been about 10 years since I've been on snowboarding, which I was a little bit nervous about, but ended up all right. That's the views from top. It's actually a great time to go skiing on the mountain. Immediate from I went there about 2 hours to get that's me and JFK pretty easily. So this wasn't a complete boondoggle. I was actually there for a Cloudflare event. They have a relationship with the U.S. ski team. You can see some of them right there. And they provide technology to them and work with them as far as helping them train better. It's pretty interesting to hear about their effective walk. Working with athletes, you see this a lot. You see a lot of this Arrival, 1, as far as stuff like cloud providers ever.
So when do we want to lead?
And then right there in the
theoretical point of view, so from a trying to play optimally point of view, essentially we want to lead flops that hit our range better than his, even though his range contains aces, which is like a universal best hand. So they're rare, but they do exist. And I think it's okay if you never lead, but I'm going to quickly run through this section, showing some examples where I think leading is fun. But I think it's an advanced, unnecessary play. So here's an example. I hope this is visible. So we're pretty shallow here. So most of the situations where leading is good, you're fairly shallow. So cut off 1 from the button makes it 1200 at 300, 600, and there's antes. So we call with 9 deuce suited with 4.5 to 1 odds. Okay, so here we flop 2, 5, 6, and I lead a third of pot, planning essentially to get all my money in. Because we're so shallow. Like, I only started the hand with 10 big blinds. Essentially, any pair is going to be good enough to get all my money in. Although, maybe not if you raise from under the gun. But from cutoff, I'm happy to put all my money in against this. So what's the rationale? So our hand's good enough to put all our money in, and it's essentially a better flop for our range because we're short enough where the the immediate equity preflop means so much to us that we're calling a very wide range of hands. Basically, a lot of hands that includes 2s, 3s, 4s, 5s, and 6s, whereas his range, he opened from button, so he opened from cutoff. You know, even though it contains more monstrous hands than ours, like pocket aces, it also just contains a lot of hands like Jack 10, Queen 10, basically hands that don't connect with this board, because if he had 6-5, he probably isn't going to open. At least I don't think by my recommendations he should be opening 6-5, whereas we can have hands like 6-5, we can have hands like 4-3. So I lead here. So it's basically essentially saying, you know, I'm no longer respecting you because the flop came in a very specific way where now my range of hands is actually better than your range of hands. So I'm essentially the pre-flop aggressor. I'm going to bet and try to make the pot big and force you into a tough situation with your weaker range. And yeah, and we can play like this with our good hands and with our bad hands, like 7-3. We have a gut shot, but we can bluff with it. So here's another example. So under the gun raises, we call with ace-9 suited, which I think is a bit speculative, but whatever. We decided to call, and we lead a 10-7-5 flop where we have a flush draw, and once again, I think it's reasonable. So it's deep, it's fairly deep, but we can have, even though they can have aces, we can have more hands like, we can have more pocket 5s, pocket 7s type hands than him who might not open those. And also, he almost certainly isn't ever going to have 9-8 of diamonds or Jack 9 of diamonds, hands that are basically monstrous draws, whereas we can. So once again, I bet because I don't really want him to check back ace-king or pocket 8s or something, which he probably will because, you know, if they have ace-king, they're going to think the board is fairly scary. They're probably not going to fold that much because there's so many draws if I bet. So they're just going to check back ace-king. And that essentially has two problems. Is we're not beating ace-king unless we improve. So by betting, we just make the pot bigger against ace-king and 9s, and we can get them to fold. Whereas if we check, it might just get checked down. And yeah, so yeah, one caveat about leading though is if your opponent knows leading is part of your strategy, then your range is significantly weaker when you actually check. So as a result, if your opponent knows you're the type of player who, let's say on a, you know, so this is really getting next level, but if they know that you're the type of player who will lead a lot of your hands on a 2-5-6 flop in this specific situation, then when you check to them with a hand like Jack 10, they can basically just bet and know you'll almost certainly fold because you're leading a lot of your good hands. So that's another caveat about leading. It's very tricky to balance correctly because you need to, you know, if you're leading bluffs, you need to also lead some good hands to balance it out, but then you also need to check some good hands occasionally to balance out all the bad hands you're checking so that your opponent can't just bet for free. So it's a very tricky play. I wanted to quickly run through it to just say it's out there and, you know, when you watch poker and you see people not automatically check to the pre-flop aggressor, sort of give you an idea of why. But it is a fairly advanced and tricky play, and it's easy to make mistakes leading, which is why I think, you know, I think it's fine if throughout this course you never lead. Okay, so now I'm going to talk about some implied odds and reverse implied odds. So here's the situation. So note that, so we have the worst hand in poker. We've got but we've only got 3 big blinds, okay? And hijack raises to 2,400. So the question is, do we want to call in this situation? So we're putting in 1,600. So we can do a quick equity calculation. So if we call, we're all in. So the only thing that matters is the equity of our hand against his range. That's essentially the only thing that matters. Because he has no more decisions. So optimal play doesn't even matter in this case. It's a strict mathematical expectation calculation. And we're actually, so we need to call it 2 big blinds. So 1,600, that's 2 big blinds. To win how much is already in the pot is 5.5, right? 5.5 big blinds. So they made a big raise here. They made it 3x. So we need 2 over 7.5, which is 27% equity. And if we put them on a reasonable range from that position, we have 28% equity, which is enough to call. So I think calling is a fine play. Okay, I'm not making fun of this person, who I think probably was me. So yeah, calling is a fine play. And So now, but I want to emphasize, okay, so if calling is a good play because it's positive expectancy, why don't we call when we have more chips? So in this situation, if someone called, they would probably be ridiculed, right? Why are you calling with 2-7 offsuit against a hijack raise that isn't even giving you good odds because they've raised it 3x, which is a big raise. So why is it bad in this case when you have more chips? And the reason is essentially what's called reverse implied odds. So in the first situation, we called because we were all in and the equity calculation said we could.
If a donation
But in
makes
the second
sense for you right
situation,
now,
even though the
I'm
equity
asking-
calculation is the same and we do have the right odds to call pre-flop, the hand isn't over. There's still potentially 46,000 more chips to be put in post-flop. And with a hand like 7 deuce offsuit, it's not only is it a weak hand, it's very hard to play. When we hit a pair, we hit a small pair. We're often not going to be sure whether we have the better hand. We're going to have to decide whether to fold or call them down, and we're often going to be wrong. So it's a very, very easy fold in this situation, even though you have the odds, because these reverse implied odds hurt you so much when there's still potentially 46,000 to play for post-flop. Okay, so here, let's say instead of 7-2 offsuit, I had ace-2 offsuit. I would still fold. So if you do the same equity calculation, we actually have 43% against his range, which is tremendous. But you only need 27% equity to all in, right? So why would we fold when we have 43% equity and we only need 27% equity? The reason is because, once again, reverse implied odds. So there used to actually be this way you could cheat in online poker. So they had this thing called disconnect protection, which is if someone disconnects, this is really stupid. And I got cheated by this so many times. Basically, if you disconnected, instead of your hand getting folded, essentially there's no more betting and all the cards are dealt, and the person who wins the hand just wins the pot. Okay, so essentially by disconnecting, you could say, okay, screw you, there's no more betting, we're just going to see until the river, and whoever wins the hand is going to win the whole pot. So basically you could cheat in this situation even if you had 7-2 offsuit by just calling and then disconnecting immediately, and then none of this reverse implied odds exist. But you can't cheat like this anymore, so don't try to make that play. So yeah, so in this case, even though you have 43% equity, I would fold. Here with 9-8 suited, it's a whole different story. We only have 37% equity, which is worse than 43%, but I would call. With 9-8 suited, you can make a flush and make a better hand than him. You can make a straight and get him to put in a lot of money with a good pair. And yeah, you're still out of position, you still have to act second, but overall it's just a much better situation. Okay, so now I want to talk about implied odds. So with the 9-8 suited, I sort of talked about it's the implied odds, the fact that you still have to play for more chips after on the turn and river almost works in your favor, because you can make straights and flushes and have a very good hand and be fairly certain you're winning and get him to put in more money with the worst hand. So implied odds is basically, it's when the odds are in your favor because you're playing a hand that plays well post flop. Okay, so let's look at an example where implied odds I think are good. So
Klaus, and hello to everyone in beautiful Davos. This has been a truly historic week in the United States. 3 days ago, I took the oath of office, and we began the golden age of America. The recent presidential election was won by millions of votes, and all seven, every one of them, all seven swing states, it was a massive mandate from the American people like hasn't been seen, and lives are being lost.
Mr. President,
hello.
What great honor, and pleasure to welcome you back to the Davos community. Just 4 days into your new mandate, we highly appreciate your presence with us today. We wish you all the best as you take on your critical work ahead. The global challenges we face today are monumental. The importance of American leadership and your personal leadership in this regard is fundamental and paramount. We are here to hear your vision and policies related to revitalizing the economy and addressing the global challenges. As you might expect, Mr. President, your return to office and your forthcoming policies have been at the focus of our discussions this week. The discussions among 3,000 political and business leaders from over 130 countries who came together here in Davos. We look forward to hearing first from you and then to the follow-up discussion with business leaders moderated by my colleague Børge Brende. Ladies and gentlemen, the President of the United States, Donald J. Trump.
So this is called set mining. This is a play that's, I think, so I'm going to go through it even though it's a play that's sort of dying in poker. I think it's a play that no longer works that well in practice nowadays, at least at at fairly high stakes. But it's, in theory, I think it teaches you a very good thing about implied odds. So in this case, under the gun raises do 3x, 2400, when the blinds are 400, 800, and we decide to call. So if you do the calculation, we don't have enough equity to call. But why do we call? So essentially, we're in position because we have the button, and also we can win essentially a huge pot when we hit a third deuce. So now, this only happens a small percent of the time. If you do the calculation, this happens roughly 1/8 of the time. You're going to hit a third deuce 1/8 of the time, and essentially when you don't hit a deuce, you're against an under the gun raise, so he's going to have a really strong range. You're going to lose the pot 7/8 of the time, essentially, roughly speaking. So what this is essentially saying is, if I'm only winning the pot 1/8 of the time, I need to win on average 8 times as much as I lose for it to be worth it, right? But the point is, at least back in the day in poker, you essentially do. Because when you do hit the deuce, they're going to have pocket aces or pocket kings, or, the flop will come ace 6-2 and they'll have ace king. They'll just have a tremendously good hand that's still crushed by your hand so often that you definitely, essentially 1/8 of the...
What you want to do is save hundreds when Liberty Mutual customizes your car insurance.
That's great, but can you ask your...
What's the difference between your mad mate and, oh yeah, I know about that? Knowledge. That's all there is. That's the only difference between the two reactions. Whether you are a Muslim, or whether you're a Hindu or a Christian or Jew, whatever, whether you're left or right or center, whatever your culture is, you're all being manipulated by the same force. They have no interest in a world of love, a world of joy, a world of happiness and peace. They want constant emotional and mental upheavals. They want wars. They want deprivation. They want suffering.
Hi everybody and welcome back to Getting There, the podcast. Now today's episode is one I've been thinking about for a very long time. Whether you agree with him or not, whether you've followed his work for decades or this is the first time you're hearing his name, David Icke is one of the most polarising, persistent voices of our time. A man banned from over 30 countries, removed from platforms, censored, ridiculed, written off, and yet somehow he is still standing and still speaking. He's still refusing to bow down to the pressure of a world that has tried again and again to silence him. And before we dive into the theories, the systems, the global agendas, the AI revolution, I want to start somewhere human. What does it feel like spending your life swimming against the tide of public opinion? What does it do to a person to hold ideas that most people are terrified to even look at? And why does he keep on going? In this conversation, we go far beyond the headlines. We explore consciousness, the nature of reality, the limits of human perception, the possibility that AI may already be conscious, and the idea that our history, our origins, our knowledge, our potential has actually been deliberately hidden from us. We ask whether we're living in a simulation and whether ancient civilizations knew more than we realised, whether humanity's evolving or being engineered, and what this moment in history is actually asking us. This is not an episode about agreeing or disagreeing. This is just about curiosity. It's about asking the questions that most people are too afraid to ask. It's about challenging the narratives that we've been handed and exploring the ones we've never been shown. So, I encourage you to sit with an open mind, challenge what you think you know, and join me in a conversation with a man who's spent his entire life trying to break the boundaries of human perception. This is David Icke. David, you have spent decades standing against governments, institutions, media, technology, and entire global systems that most people are actually too terrified to even look at. You've been banned from endless countries, you've been banned from Australia, YouTube, you've been deplatformed, ridiculed, scrutinised, and yet you've never backed down. But how are you? Like, how are you? Are you exhausted? Are you tired? Is this shift fueling you? Human to human, like, how are you coping with everything?
No, I'm very energized. I guess it comes from self-identity. We are manipulated to have a limited self-identity. For instance, we are encouraged to identify as a human. And if you identify as a human, not as an experience, which is what we're having, but as an I, then you're identifying and you are self-identifying with limitation. If you follow a religion and you think you have a soul, and that you are being judged by some judgmental God, in the Old Testament version, a real bloodthirsty, bloody tyrant, then you are subordinate to the God, and you are subordinate to the limitations of being subordinate to the God. I don't see that. I don't see myself in those terms. I see myself as an expression of infinite awareness, of an infinite consciousness that is everywhere, and I'm just an expression of it. And so I don't identify with limitation. I don't identify with being human, and therefore I don't identify with the limitations of human.
So then,
so I just get on with it without thinking, oh, I'm 73 now. Yeah, I can't keep going. Oh, you watch me. You know what I mean?
We're watching you. It's like it's all going up another gear. But do you ever question? You've quite clearly got a message. Do you ever question why it was handed to you more than anyone else?
Well, it's a kind of an interesting story of how this all started for me, because I was born in Leicester in the English Midlands, and I was born into a council house where my brother still lives, and we were skint, to say the bloody least, and you had this feeling that, well, kind of, this is my lot. And then, because I was a very diffident kid, you wouldn't know it now, but I was. And then I started doing well in football, and I got picked for the school team, which kind of shocked me. You know, I thought, hey, you know, good things can happen to you, you know. And then I went on and I became a professional footballer, because the moment I got in the school team, I know what I want to do. I want to be a footballer. And people were going, oh, yeah, of course you do. Yeah, what's the chance of that? And I thought, I'm going to do it. And then I got into football, and I finished with arthritis, and I went into journalism, which was always my second love. And then eventually in the BBC, and I became a national spokesman for a while, short time, for the British Green Party. Then one day, I'm still working for the BBC as an anchor, sport news anchor, and I was still then a national spokesman for the British Green Party. And I was with my son, Gareth, who's a big strapping lad now, of course, works for Iconic with me, but then he was just a little boy. It would have been 1989, maybe, 89. And where I was living was near the seafront, Ryde on the Isle of Wight. And there was a cafe there, like a Greasy Joe cafe. So we were going to go into this Greasy Joe Cafe. And it was packed, so I said, come on, Gaz, we'll go up the town, get some lunch there. And then this railway worker, because it's a railway station on the front, came up to me and started talking to me about football. There's a big semi-final that day of the FA Cup. So we chatted for a bit, and then I realised Gaz wasn't here. So I knew where he would be. He would be in the newsagent shop we were standing next to, because they have steam train books in there, or had, and we like steam trains. So I knew where he would be, so I walk in to the shop, stand at the entrance, and there's Gaz looking through the steam train books. I said, come on, Gaz, we'll go up to town, get some lunch. And at that point, it was like the atmosphere changed. Like the electromagnetic field, technically, changed. It's like, not quite that I was in another reality, but the atmosphere had definitely changed suddenly. And then I felt my feet being pulled to the ground, like magnetically. And I'm thinking, what the? And then this, no, it wasn't a voice, it was like a strong thought form went through my head and said, go and look at the books on the far side. Now, I knew this newsagent shop, was going in there all the time. The books on the far side were Mills and Boon bloody novels and Barbara Cartland for the tourists in the deck chairs on the beach. What do I want to go there for? But of course, I'm in a bewildered state, and I went across, and in among the Mills and Boon was this one book that stood out because it was different. It had a woman's face on the front. It was called Mind to Mind. So I picked it up and I looked at the blurb, and the blurb said psychic. It was the biography of a professional psychic called Betty Shine, who lived near Brighton. Now, why this was highly significant to me, that moment, was because from the start of 1989, this would be the early part now, like the spring of 1990. I'm in the shop as my memory comes back. From around the start of 1989, something very strange had been happening while I was working for the BBC and the Green Party. Every time I was in a room alone, it was like I wasn't alone. It was like there was a presence there. And all this was new to me. I hadn't been into any of this stuff before. And this continued through 1989 until just before, it was actually days before the book incident in the newsagent, that I'd been working for the BBC in Shepherd's Bush in West London. And I went back to the Kensington Hilton Hotel, where I was staying overnight. And I sat on the side of the bed, empty room, and this presence was so bloody tangible, you could touch it. And I said out into the room, look, if there's something there, would you please contact me, because you're driving me up the bloody wall. So then a few days later, the book incident happened, the bookshop incident happened, or the newsagent. And so I'm stood there, and when I saw the word psychic in the blurb of the book, my immediate thought was, I wonder if this lady would pick up what the hell's been happening to me for the last year. So I read the book in 24 hours, contacted her, went to see her, and what I said to her was, I've got arthritis, finished my football career, maybe your hands-on healing, which she also did, would help. I didn't tell her anything else, because I didn't want to lead her or give her any idea of what was happening to me. So I went to see her the first time, had a nice chat, bit of healing.
Little Reiki.
Second time, yeah. Second time, same. Third time, I'm sitting on this bench in her front room, and I felt like a spider's web on my face.